Good morning, hello, and welcome to the coding train. Whoa, that was like I had my finger over this little air hole here and I got a higher pitched sound. Amazing. Science. My name is Daniel Schiffman and I'll be your host this morning on a Wednesday, which is every Wednesday. I will say thank you for being here at this regularly scheduled time. I have been so consistent about this. I'm amazing myself. However, I will report to you that there will be no live stream next Wednesday. I'll be back 2 weeks from today. So let me just say that from the outset. I have a trip planned. I got some stuff going on. But don't worry. Underneath here in my coding train oven is cooking a whole set of videos about working with data and APIs that you have not seen yet, because I have been recording a bunch of videos not during a live stream as an experiment. But that's my little pitch. If you want to join the coding train as a patron or a YouTube member, you can get some sneak previews of that stuff. Also, a big shout out and thank you to Brilliant.org, who is the sponsor of today's live stream. On Brilliant.org's homepage, you will see a challenge about relativity, classical relativity. We also have the term special relativity, general relativity. Oh my goodness, my mind since last Wednesday, I think it was last Wednesday, right? When the first image of the black hole came out, has just exploded with wonder and awe at the universe we live in. And I've been spending a lot of time reading some papers, watching some YouTube videos. I am not a physicist. I do not have a background in that. But I have been sent down, I was going to say rabbit hole, but I think the appropriate term here would be many black holes. I have not emerged. By the way, once you're in it, there's no way to get out. I am past the event horizon. Get me out of here. But so that's what I want to do in the first segment of today. So the first segment today, I'm going to talk a little bit about the recent black hole image and do a very crude kind of nature of code style physics simulation of light approaching a black hole. But I will be using Newtonian physics, and so it won't actually be accurate, but I will talk about what's missing there and a little bit about relativity, and then kind of like pose that as a challenge to you to think about, and maybe next week after I've had more time to read these papers and crunch some of these numbers, maybe I can come back and make it more accurate or such. The sound, once again, I take over the chat. I see the sound sync is off. I don't know, someday I'll fix that. I apologize. Also, so then, segment 2 of today's live stream. Look at this, I have a plan and everything, and I'm sure it will go haywire. Technical problems I'll be stuck in the black hole for 4 hours and never get to the next part, but this is my plan. Segment 2, I am going to program the data structure, a stack, and look at a quiz that's actually, if you go to brilliant.org/codingtrain right now, it'll take you to a page, which is a quiz on stacks, and there's also a quiz on queues, and this is part of some new computer science course materials that Brilliant has, which has been really terrific for me to review a lot of the stuff that maybe I did 15 years ago. So it's wonderful for both kind of continuing education for me, like I can like look at this stuff again, or when I was saying on the Slack chat this morning in the Coding Train Patreon group that the last time I think I had to implement a stack, like actually implement it without just using kind of using an array as a stand-in for a stack or some other stack from a library, was probably 15 years ago. So I'm going to attempt to do that today and look at programming my own stack data structure in the context of that quiz and kind of leave that as a challenge to you to take the quiz. And then pending time, I will have to say this, it is in the title of this video, which I probably shouldn't have put it there, but at a minimum, I will show you some new examples that I'm working on that do NeuroEvolution with TensorFlow.js. I would love to do a coding challenge around that. That might come the next time, but at a minimum, I do have a few like finished examples that are basically ports of some of my previous examples. There's a steering one and a Flappy Bird one that I will show you. Please say this dot once. I'm just pleased that you didn't ask me to like say this dot and dab or something, because that's really just not a thing. Not a thing. Not a thing. This dot.
As always, I always forget this dot, this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do dot, this dot.
I am your entertainer. Give me your instructions and I will entertain you. I think we could just get started. right? What else I don't have anything else to say in my introduction. I'm like efficient and organized. I'm like a professional YouTube live streamer person. This won't last. and there's nothing, it wasn't even that good. Okay. So here we go. So I want to talk about a couple, no, I remember what I wanted to say now. Links are in this video's description. So I want to mention a couple things. I think, let me just find it. I have it over here. Well, let me pull up today's live stream. This will be fun. So here we are. Well, there's 668 people watching. Okay, so I want to talk about two things. One, I want to mention a huge thank you to Chris Orban and STEM Coding. Chris Orban from Ohio State University runs a wonderful YouTube channel called STEM Coding with a lot of P5.js and other coding activities themed around physics with real science. Like me, I do my I don't really understand it, but I'm going to try plugging this into this and plugging this into that. Maybe it'll work. But you've got science people, and there's PhD students and graduate students, a wonderful diverse array of presenters on that channel. So I highly recommend you check that out. The reason why I'm thanking Chris in particular is Chris wrote up this wonderful guide, which I just, it's actually called Simulating a Black Hole. So one of the coding challenges on the STEM Coding YouTube channel is a coding challenge called Slingshot with Gravity. And it's very similar to some examples I have in the Nature of Code book about looking at gravitational attraction and simulating that in a 2D world using Euler integration and kind of simple. I don't know why I'm using. I'm gonna use a fancy term using some basically x equals x plus speed kind of code to simulate how bodies interact with gravity. So Chris modified the code to kind of talk about black holes a little bit, and there's some nice information in here and a lot of explanation. A really nice formula here, which I will talk about for the radius of the event horizon. The Schwartz, so otherwise known, sorry, as the Schwarzschild's radius. I was trying to think, how do you pronounce that? It's spelled Schwarzschild, but I think it's Schwarzschild. It's very hard to say. It's like a tongue twister. So I'm going to come back to this when I do the video. So I also wanted to just plug, if you are a teacher, a wonderful thing that is happening this summer is called the Pathfinder Summer Institute, which is professional development in computer science and making at Indiana University Bloomington from July 14th to 19th. So if you are a teacher and you're interested in this, please apply. I'm happy to help. You can reach out to me, but I would suggest probably reaching out to STEM Coding or Chris Orban on Twitter to ask any questions about how this works. All right. So I wanted to mention that. Here I am mentioning that. Is there some kind of theory of relativity going on here with space-time? I'm curving my space-time into myself in the past. Oh, I'm not even, this isn't playing. I'm frozen. Be live. There we go. Oh, I was trying to get to the part where I curve. Go, 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 go. There we go. I'm going to bend space-time. You could do it. Are there really there's got to be less than 500 people watching now, right? Come on. Come on. There we go. This would get this. Boy, I'm so behind. All right, I'm going to give up on this. Oh, there it's happening. Okay, I'm giving up on that. All right, so let's see. Let me get out P5.js. Let me log into Coding Train. Let me go to high contrast and set the text size to 36 maybe. Let's see if I can get away with a bigger
window here, black hole. Okay. All right, I think I'm ready to go. Let me check chats. Yes. By the way, Simon, I see in my little message box here, Simon Tiger is typing. Something will be said soon, but you should check out Simon Tiger's YouTube channel as well, who has also recently made some videos about black holes. Yes, that's a good point. Yes, Simon says, come to the whiteboard, then back to the screen, and then bend space-time. I'm learning about how my feet are younger than my head. Boy, it's amazing. This like, my mind is blown. All right, let's go over here. All right. So let's see, how am I going to start this? This. It's from 1978. All right, I think I have everything I need. So, image of black hole. What's going to be a good, is there a, let's try this. Okay, start with this. And then what's the name of the group of, it's the Event Horizon, like the name of the group of the 200 scientists. I want to like reference that. Remember how I was all prepared and had a plan? Event Horizon Scientists. Like it has a name like that. The Event Horizon Telescope. Maybe that's what it's called. Event Horizon Telescope. Okay, about organization. Yeah. EHT, Event Horizon Telescope. Everyone's telling me. Great. Okay. Thank you very much. Oh, someone asks, are you going to simulate a 2D section of a 3D black hole, or rather a genuine 2D black hole? Because the physics are very different in 2+1 dimensions. All right, so I would say the answer to that question is neither. I'm not really going to do anything remotely close to accurate. I'm going to talk about what I've learned in terms of looking at some of these resources, and I'm basically going to just do a Newtonian gravitational attraction example, but kind of consider one body to be the black hole and the other body to be a single photon or a beam of light, and look at how that light curves as it approaches in 2 dimensions. But this will basically be not accurate because it's sort of like assuming only classical relativity, and I would need to think, and I need to like look at a part 2 would be to revise this to actually be accurate. But I think the idea the story can be told, and it'll be an interesting kind of prompt for the audience who has maybe a rigorous scientific background to contribute here. So that's kind of my plan. So if people are joining because they're going to see some kind of black hole simulation, prepare to be disappointed. Welcome to the coding train, where our motto is
Prepare to be disappointed. Bing! I need like a little effect. I can press a button, a little glistening, winking. By the way, I cannot wink. I cannot wink with my right eye. My family finds this hysterical. This is me in front of a black hole image, attempting to wink with my right eye. If I were inside a black hole, you would not be able to see me doing that, nor would I be able to communicate with you. I would also be very, 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 very dead. Or maybe not. Maybe I would just be millions of years in the future. And I would be Matthew McConaughey. Yeah, okay. Let me cycle the cameras. Hello, and welcome. Hello, welcome to a coding challenge. Simple, very crude, not so accurate 2D black hole simulation. So I'm fascinated by this image which appeared on the internet a week ago from the Event Horizon Telescope group of scientists who produced this image with many different telescopes all together, timed with some kind of like bazillion time precision to create this image. There's over 1,000 people watching? That's not a record. I have never broken 2,000, but oh, it's not classical relative. By the way, Simon is giving, sound effects are a little, okay, hold on, so much is coming at me at once. So I'm told the sound effects are a little bit loud, so I'm going to turn that down. Maybe that's a little bit better. Simon corrects me saying it is not classical relativity, it's classical mechanics. It's based on Galilean relativity. Okay, thank you very much. Tech Writer's asking, how will that include NeuroEvolution? It will not. NeuroEvolution is the third segment of today's live stream. I mean, I would love to neuro-evolve a black hole, but I don't think that's going to happen. Everybody's telling my audio is out of sync. I can't do anything about that. I apologize. The good news, I would suggest, if it bothers you, turn this off. Go do something else. There will be an edited version of the sort of highlights, if there are any highlights, of today's live stream that will have the audio sync fixed. By the way, does everybody have the audio sync problem? When this has happened in the past, I've been told that some people have it in sync. Hit me, baby. No, that's Britney Spears, whatever. Some people have it in sync, and some people have it out of sync. In before pronunciation complaints. Oh yeah, I'm sure I pronounced however you say the Galilean. What did I say, Galilean? I think we should be able to say it the way we want. First of all, GIF. That's how I had to say to you, you GIF-alalian mechanics people. Oh, I gotta start this. Everybody's telling me it's out of sync. All right, it's out of sync for everybody. All right, all right, here we go. Hello, and welcome to a coding challenge. Simple, very crude, not so accurate 2D black hole simulation. Now, I became interested in this topic a week ago when this image, the first ever image of a black hole produced by the scientists from the Event Horizon Telescope, made this thing. And it's amazing, and I will include many links to explanations and papers that you can read up more about how this image was made. And so I became fascinated with this idea, and sort of like in the sense that I have this book called Nature of Code, which has a bunch of examples about how to look at the formula for gravitational attraction and then make a little 2D simulation of that. could we demonstrate some of the ideas in how this image was produced, in how a black hole behaves, in how a black hole bends space-time, or how space-time is bent around a black hole, and how light can't even escape, and the speed of light, and then there's relativity, and there's special relativity, and oh my god, all this stuff. There's so much stuff. Now, as you know, if you've watched this channel before, I am not a physicist, nor do I play one on YouTube. And so this is not something that I would ever even come remotely close to claiming to be an expert in. So I am relying on the good-heartedness of the internet, in particular Chris Orban from the YouTube channel STEM Coding, which has a lot of wonderful coding challenges and video tutorials related to real science and P5.js and teaching about science through coding with a diverse set of speakers, graduate students, and various other people. So I highly recommend you check out STEM Coding. And Chris Orban, one of their examples, has slingshot with gravity, a demonstration much like my gravitational attraction nature of code example. That's what I'm saying, that's what I'm saying, that's what I'm saying. Edit, 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 edit point. Edit point, don't move, otherwise it'll be hard to edit. Don't move, otherwise it'll be hard to edit. Moving. What was I going to say next? So Chris recently, when that image came out, made a slightly modified version of that example to talk about some of the basic mechanics of how a black hole behaves. And there's more explanation on this page, and you can link here to see the modified P5.js code. So I highly recommend you check that out. There's also a wonderful video by Veritasium. Wait, did I say that right? I couldn't say Galilean. Wait, hold on. There is also a wonderful video by Veritasium, which actually came out before the image was released, which is kind of amazing. Then there's also a follow-up video of when the image was released. If you don't know the Veritasium YouTube channel, I mean, if you know this channel, you know that channel, probably. Anyway, that has this image in it, showing how the photons, paths, rays of light bend around a black hole. It's like so insane that they bend around, meaning if I'm standing, I mean I couldn't, but if I was standing on the black hole, I could see the back of my head because the light would bend around it. So I want to see if I can create something along the lines of this to demonstrate that idea. This is like a tiny little inkling piece of the puzzle of all of the science and work that went into producing that image. So I'm going to do this. I'm really just going to use Newtonian physics, basic mechanics. I'm not going to get into relativity and kind of modifying how time slows down the faster you're moving. What did I just say? Yes. I'm not going to get into special relativity and how time slows down as you're moving fast. So I would like to come back to that. What I would like to do is just make something that gets at this central idea. And then as a challenge to you, I hope you will modify it. I'm going to give you some resources to how to look into more of the science of how it actually works. And then maybe I'll come back next time and do a follow-up video. And in theory, I could just keep going with this and make it 3D and then actually try to model how that image was produced. This could go on forever. I don't know how far I'll get, but you, the viewing audience, hopefully will take it from me and make something wonderful, which then I can share. I'll include links to these other resources in the video's description, and some of these came from Veritasium. I'll include links to, what was I trying to say? Veritasium. It's very hard to say. I will include links to other resources for you, some of which I got from the Veritasium video as well, that you can read up on, and I'll be reading these a lot over the next week or so as well. So one is you should check out this How to Draw a Black Hole, which goes through a lot of the math and then some nice, really computer graphics, shader-style 3D tricks that you can think about looking through. And you've got something here that actually looks quite a bit like the artistic rendering of a black hole in the film Interstellar. So I highly recommend you check out this article by, I'm sorry, I don't know the person's name, by Ratanels on GitHub. You can also read this 1979 paper image of a spherical black hole with thin accretion disks. I'll talk about what accretion disk is in a moment if you're not familiar with it, but you can see kind of some of the math about the photon trajectories. And so some of these formulas would help me make, they're over here. Some of these formulas would help me make what I'm about to do a bit more accurate possibly. And then, this was something that was sent to me by Kay Wiekman in the chat, which has some of the formulas, also the equations for the radial motion of photons. So I'm going to do this without implementing the with any kind of scientific precision, just to kind of get at a framework. Am I apologizing and giving you enough caveats? I think that I am. Ready to move on. I took some notes. I watched Veritasium's video and I took some notes. All right. Okay, let's diagram the sort of elements that I want to consider in my simulation / visualization. And of course, the real world looking. Oh, 1978. Hold on. Whoa, it says 19. Oh, the book is 19. All right, sorry. Correction, the paper is from 1978. Here, Mathieu will dub this in when the edited version comes out. 1978. From 1978. 1978. There's a few audio samples you can dub over me saying 1979. Does the coding train read chat? Asks Slush Puppy. Every once in a while. You just have to get lucky, I guess. Let me try to Let me try to diagram out some of the elements of what I want to include in my part simulation, part visualization. So in 2 dimensions, let's say we have a black hole. Here's my black hole. And I'm going to do this vertically because I think that'll work. Actually, it doesn't matter. Here's my black hole. Now, what do I mean by this being the black hole? First of all, a black hole is not something we can see. That's why it's called a black hole. The reason why it's black and we can't see it is because light, the force of gravity of the black hole is so strong that light can't even escape from it. So you could not, from inside the black hole, there's no way you could communicate outwards. So that's why it appears black. It's often referred to as a shadow, and maybe I'll sort of like get to that in a sense. But but one thing it has, the reason why the force of gravity is so strong is it's massive, supermassive. And so this black hole has a mass. Now, I wrote this, I took notes. I have notes. Like, I don't know, this might be the second time ever I've done this, but I don't know where I wrote this down. It's not these notes. Oh, yes, here they are. Oh, but I could have memorized this. Now, this being, if I'm talking about Sagittarius A star, which is the name of the black hole that the image was made of, the mass of this is 2.6 million suns, give or take. I think it's, that's a sort of estimation, approximately, give or take. I think it's 0.2 on some other page on the internet that I read earlier today. 2.6 million suns, so massive. That's important. There is this idea of the event horizon. The event horizon being the path. Oops, sorry. I hope people will correct me as I get things wrong, by the way. The event horizon being the path around the black hole, sort of edge at which anything inside can never escape, including light. Nothing, right. So another sort of key element here is c, otherwise known as the speed of light. This is the fastest anything in the known universe can travel. Nothing can travel faster than the speed of light. And there is also an actual number there, which is 299,792,458 meters per second. Okay. That's going to be great when I put that into a variable, right? Here's my variable, 299 pixels per second. That'll work. I'm sure that'll work. That's going to be great. So the event horizon, now there is actually, amazingly, a formula for what this, so the event horizon, is at a certain distance from the center. We can call this a radius. This is known as the Schwartz Schwarzschild radius, which I have a real problem saying, but hopefully I'm pronouncing that close to correct, the Schwarzschild radius. Now there is actually a formula to calculate this. It's also in my notes. It is, the Schwarzschild radius is, did I not write it down? I have it in my code. Oh, it's on Chris Orban's page. Hold on. I didn't write that down. Hold on. Oh, people are telling me that neutrinos travel faster than the speed of light. All right. Oh no, this is not plugged in. Hold on. My soundboard is not plugged in. Cancel. Here we go. That formula is right here in Chris Orban's article. So we have that as the radius, the Schwarzschild radius equals 2 times the universal gravitational constant times the mass of the black hole, and divided by the speed of light squared. Okay, so we could actually do this calculation, right? We could take this number, square it. We need one other thing. We need g. We need g, the universal the gravitational constant. Okay, good. Right, not all black holes are supermassive. That's correct. Sorry, I'm referring to this black hole, which is a supermassive black hole. Wait, I want to find out the universal. Where is G written out on this page here? G, right. Okay. All right, so this is, all right. All right, so now I'm looking at G, the gravitational constant. Okay. So G, the gravitational constant, is, thank you also to Chris Orban's article, 6.67 times 10 to the negative 11 is the value for the gravitational constant. So now we have all of these values, and I could sit here and I could calculate that radius. Oh, should we do it? Could somebody do that for me? You got some kind of big calculator? I wish I had a prop. I really wish I had a prop. This would be an awesome time for me to have a prop right now. I could go over here and pull out a giant. Oh, is this the M8? Am I talking about? Are people trolling me, or did I get it wrong? And I'm not. I thought I'm talking about Sagittarius A star. Hold on. Now I have to be sure about this, right? Isn't that the one? This is Sagittarius A star, right? Okay. That's the correct black hole, right? They're also doing an image of another one. I forget what it's called. I might have written it down somewhere, but I don't remember. Okay. Wait, I'm looking at this. Okay. M87. No, but M87. Okay, I'm so confused. I thought M87 is the galaxy. Oh, I'm so confused. It's M87. Yeah, I just got confused. Sagittarius A star is the blurrier one. Oh, shoot. Oh, I didn't write that down anywhere. It doesn't matter, but it matters for accuracy. Okay. Shoot. Yeah. I don't know how to fix that, but yeah, M87 is the galaxy, the black hole at the center. That's why we say M87 star, right? star. Messier. Yeah. Okay. All right, I messed up. Let's see if I can do some kind of magic editing tricks. Yeah, okay. So a couple options would be one, this is one option. Oops, I said Sagittarius A star. Wait, no. Is that what I said? Stop, I just said Sagittarius A star, it's M87. There's two black holes that the scientists are working to get an image of. The first one was M87 star, M87 being the galaxy, and the black hole being at the center of it. And then they're also, they're working on an image of Sagittarius 87. Okay. Okay, let me try another thing. This black hole, this particular black hole, a supermassive black hole, not all black holes are supermassive, but this one, known as M87 star, named for the M87 galaxy, at which this black hole is at the center, and its mass being approximately 2.6 million suns, give or take. I don't know, Matthew, figure that out. We'll correct it somehow later. All right, where was I in this? All right, I was going to calculate this number. So as a challenge to you, calculate this number and leave it for me in the comments. Okay. So while you might think of the black hole as sort of like nothing, it's nothing. Nothing can escape from there. It's the end of everything. This is not actually the case. It's so much mass. And the reason why it's so much mass is this one is particularly active. I mean, it's like just sucking up more stuff from the universe around it. And the stuff that it's sucking up is orbiting it in what's known as the accretion disk. So I'm going to make a little diagram a little bit outside here. So this, known as the accretion disk, it's a lot of matter, a lot of space stuff orbiting around, and it's at a far enough distance that it's not being sucked in. But here on the edge, right, this is the border of where past this it will be sucked in, eventually past the event horizon from which it cannot escape. And outside here, it's a little bit, maybe it's a little bit more stable. But there's actually also a measurement of the what that distance from the center is, right? Remember, this is the Schwarzschild radius from this formula, and then the accretion disk's sort of inner edge is at breaking news. Oh, I really could have memorized this one. three Schwarzschild radii, so 3 RS. So that's what's over here. So these are things that I would first want to try to visualize, right? I could draw an ellipse in my code with a radius based on this formula. And then I could also draw the accretion disk sort of outwards at 3 times that radius. What's the next thing I want to look at? Because I also want to look at, all right, now, oh, right. All right. Okay, good. Thank you, Simon, for the... Oh, did I say Sagittarius 87? Ah, I'm the worst. It's very hard to do this. Well, actually, maybe it's not. Maybe I just have an impossible time. I got to get this section done by 11:30. That's my time. 11:30 is my break. Usually it ends up being more around noon. All right. Well, look at this. I got to allow this comment to come. Okay, there we go. All right. All right. So the next thing. interestingly enough, there's another ring that we could consider. So we've got the event horizon, we've got the accretion disk, but what is the distance at which a photon of light would orbit the black hole? After all, a photon of light doesn't have any mass. So all this matter in the accretion disk actually has mass. The photon of light traveling at the speed of light doesn't have any mass, or the mass is 0. Oh boy. Oh boy, we're getting into relativity, aren't we? But it so happens that at 1.5 Schwarzschild Schwarzschild, why do you say that? Radius, at about halfway, at 1.5, is where a ray of light, a photon particle would orbit. So the question is here, how would we look at this? If light, right, the idea of seeing something is seeing light bounce off of something and travel back into our eyes. If light travels so fast that it's barely like perceptible that time, how would we look at something so massive, so far away, and it actually sucks light into it and it can't come back? So that's why there's this idea of a shadow. So we wouldn't be able to see this if there wasn't the sort of matter and plasma and all the other stuff going around it. What we're able to see is that stuff with the shadow of the black hole. And I think a piece of what's interesting about this, a lot really depends at the angle that you're looking at. Okay. And there's so much to this, but that's a bit beyond the scope of where I am capable and want to go right here in this video. So what I want to do is diagram all of this and then imagine, maybe I'll start, I don't know where I'll start it from. I'll just start it from over here. Imagine we have a bunch of our telescopes on Earth. So right, in order to image this, you would need, as the scientists discovered, a telescope the size of the Earth. And what the scientists were able to do was use many telescopes, all perfectly synchronized, all traveling, not traveling, but the Earth is also rotating, so you have a bunch of different views to be able to compile and build this image from all of the data from those telescopes. So we could maybe simulate this idea in the most basic way by thinking of the signals from the telescope, or beams of light, traveling at the speed of light at this black hole. What would we see reflected back? How do we see the light that is passing around here? Let's see what happens. In theory, what we would see, right? So let's say, okay. In theory, what we would see, let's say we have a nice ray of light perfectly sort of aligned with the center of the black hole. It's going to move in that direction past the event horizon, never to be seen or heard from again. Something a little bit off would come like this, and the gravitational pull would pull that ray of light in. It would also go past the event horizon, never to be seen again. But at a certain point, if we get a certain point outside, it's going to bend, not go past the event horizon, but kind of end up in that orbit or spin out into infinity or something like that. And it actually so happens, this is thank you to the Veritasium video, which explains this so succinctly, that the distance there for that ray of light is 2.6 Schwarzschild radii. It's the 2.6 times the Schwarzschild radius. I don't know how to say that. So in theory, if I plug all these numbers and use my force of gravity formula, we'll see exactly this happen. Ha ha ha, definitely not. But that's the idea. We're missing an important point, which is the fact that time and space bends and time slows down. But I won't, that's for you to think about and for me maybe to come back to. All right. Okay, thank you. Oh boy. I've gotten so many things wrong in this explanation. I really need to prepare more. Okay, first of all, Simon is giving me a really excellent correction. So I'm gonna need to talk about that for a second. Thank you for that. This correction about the orbits, the difference between the light orbits and the accretion, the matter in the accretion disk. Also, the mass. So mass of Sagittarius A star. Okay. All right. M87 star. 2.4 billion suns. Yeah, oh boy. Oh boy. Mathieu, when you're looking at this later, I would be happy to come back and record some corrections or like some explainery stuff over top of this, maybe narrate it a bit because I'm making some serious mistakes here. So let me come back to this. I really got my black holes mixed up. There are two black holes that I'm talking about. I mean, I'm only talking about one. I'm very sorry. I have really gotten my black holes mixed up. This is a thing that happens to me almost every day. I can't keep track of all these black holes in our universe. The image that I showed at the beginning of this video is from M87, or the camera's going off. Look, it's a black hole. You just saw the second image, the third image ever of a black hole, because I also made one with the Rubik's Cube. The black hole that I'm talking about in this scenario, the one that the image was published, the one about which the image was published, the one that is in the image that was published, is M87 star. In other words, the black hole, the supermassive black hole, not all black holes are supermassive, but this one is supermassive at the center of the M87 galaxy. That one mass is approximately 2.4 billion suns. The other black hole that I mistakenly referred to, which is also currently being imaged, and I'm sure I'm spelling this wrong, is Sagittarius A star, which is from the Sagittarius galaxy. And that one is a bit smaller, is approximately 2.6 million suns, which, by the way, when I say a bit smaller, that's a lot smaller. Yeah. It's often for us, we often think like, oh, it's just this one's a million, this one's a billion. That's just like a little bit more than a million. But no. A billion is a lot more than a million. In fact, there's like 1,000 millions in a billion or something like that. It's amazing math. So now you can revise your calculations here for M87 star. But the math would all hold true for either one of those black holes. Now, right. Some other corrections here, some other corrections or perhaps further explanation. Number one, the photon orbit, which is here at 1.5 Schwarzschild radius, is unstable. So the photons circling around will eventually get sucked into the black hole or travel out towards infinity. And that's kind of what I'm showing here with one of these that ends up in that orbit. It's going to do one or the other. The accretion disk is a more stable orbit. I should also say that I'm saying this curves, but it doesn't really curve. See, the fabric of space and time is curved. Things aren't attracted, it's just curved. You could think of it as like if I had a flat surface here and I put a giant bowling ball in it, it would push that flat surface down and a little like ping pong ball on the edge would roll towards it because it curved the fabric of space and time. So this is actually a straight line through the curved space-time continuum. Let's get back to 2D canvas and JavaScript in the browser, shall we? Oh, it's not the Sagittarius galaxy? Why do they call these things with inconsistent names? 2,400 billions. All right. 20. I got M87's mass wrong. Pardon me. Actually, this is not correct. Approximately 2,400 billion suns, which is quite a bit more than 2.6 million suns. A lot more. Super massively more. Yeah. All right. Milky Way. Yeah, okay. Here we go. Did I get it wrong? Trillion? Is that not? Okay, I see your other correction, Simon. The black hole is unnamed. The black hole is Sagittarius A star. Got it. 6.5 billion solar masses. Okay. 6.5 billion. 2.4 trillion sun masses, not the black hole. That's the galaxy? Ah, so confusing. It's the mass of the galaxy. Ah, okay. I did kind of look this stuff up. I just kind of... Let me correct this one more time. I think I would get it right now. Do you like watching videos where the information is incorrect for a while and then it just keeps getting corrected? That's not good, I don't think. All right, I have an idea. Stop! I have traveled to you from the future to come back into this video to correct what I just said, but I'm actually recording this later, so it'll look a little out of place, but that's totally appropriate for this space-time continuum stuff. To be clear, I named the incorrect black hole. So I named a black hole called Sagittarius A star, which is a black hole in the Milky Way galaxy. And the scientists are currently working on getting an image of that. And that's a smaller black hole, about 2.4 million times the mass of the sun. Something like that, 2.4 million suns. This black hole, the one that the image was published about and that I want to talk about in this video, is called M87 star. Now, M87 is the name of the galaxy. The black hole itself is unnamed, so M87 star. And its mass is 6.5. Oh boy, I gotta go wash my hands. Its mass, sorry, I should not use my fingers. Its mass is 6.5 billion suns, okay, solar masses. So it's big, really big, 6.5 billion, being a lot more than Sagittarius A star, which is 2.4 million. There we go, returning to the scene of the crime where the wrong stuff will be written for a while and then it will suddenly appear correct again. Yeah, my Google was for the entire galaxy. It's not M87 star? It's just M87, unnamed, right? Yeah, there's no M87 star. Did I say star? That's a mistake we can all live with, right? I did talk about the unstable orbit, Simon. That will make it in. That will make it in. I mean, just in case, I can say. Oh, they already have the image published already? Well, whatever. I'm behind. I'm behind the times. Oh, right. I put a star. Maybe I didn't say star, but I put a star there. Sorry, no M87, sorry, no star, just M87, that's the name of the galaxy. Sagittarius A star is the name of the black hole in the Milky Way galaxy. This is unnamed. Maybe it has a name by now. I'm sure I'll hear about it in the comments. Okay, it's the programming that is important, you think? Oh, it is M87 star? Who knows? Who knows? No. The star means it's something interesting and anomaly. The black hole is unnamed. Okay. All right. Okay, we're going to move on to the code now. Wow. Okay. All right. Oh, here we are. 300 light years later, here I am about to maybe write some code. So let's see, we need some variables. Number one is we need the speed of light. 299, 792, 458. There we go. Oh, I don't need the commas, right? Because, you know, this is code. So there we go. There we go. Now we got the speed of light. Excellent. Things are going very well so far in my coding. Now we need the universal gravitational constant, g, which is 6.67 times power 10 to the negative 11. Yeah, what could go wrong there? This seems exactly right. There we go. Now I need to have my RS, my Schwarzschild radius, which is 2 times g times, oh, the mass. Okay, now I need a constant m is the mass. That was 6.5 billion. That's no 2 zeros, some more zeros, some more zeros. I don't know, how much is the mass of the sun? Mass of the sun. Okay. All right, you see the folly here. One folly here is while these numbers are incredibly meaningful and important, they're not going to do me so much good here in my P5.js web editor JavaScript program. So what I'm going to do is make up some numbers. We're going to create our own two-dimensional universe that has a speed of light, that has a universal gravitational constant. And in fact, rather than put the mass of the black hole right here, I'm going to make a black hole class. So let's just arbitrarily say, like, do something approximating this. Like the speed of light is 30, and the universal gravitational constant is like 6. Why not, right? So, and now let me also go and make, I should have done this beforehand. Let me also go and make a, black hole.js file. Oops, black hole.js. And I'm going to add that to my index.html. And then I'm going to say, class black hole, and I need a constructor which has an xy. We need an let me use a p vector for this. So I'm going to say this dot position equals create vector x comma y, and then I'm going to do a function. And then now, and this now I need a mass. This dot mass equals 6.5. Our measurements are in billions. 6.5. And then its radius, the Schwarzschild radius, is, 2 times g times this dot mass divided by c times c. Now I need a little more space here to be able to see more code, but fortunately actually I can do this. And let's put these in parentheses. And so now what I can do is I can write show. And what am I going to do? Let's make fill 0. Let's fill in the black hole with the color black. Let's draw a circle at this.pos.x, this.pos.y with the Schwarzschild radius times 2. And so now, and I guess I might as well pass in an argument here for mass. If I were to, in my main program, say, let black hole, let's call it at M87. We're going to call our black hole M87. M87 equals a new black hole. I'm going to place it at sort of like the top, actually the left of my canvas. So let's place it at like 100, 320. And we're going to give it a mass of, what did I say, 6.5. And then I'm going to say M87.show. Do we have a black hole? RS is not defined. This dot, this dot, this dot, this dot's on. There we go. That fixes that. And where is my black hole? I guess my black hole has sucked all of the light out of it so I can't see it. Let's take a look at what this .rs is. Way too tiny, right? So my units are really kind of all over the place. So let's make some units that make more sense for our pixel space. Let's make the mass of the black hole probably much bigger, like 6,500. There we go, look! Thank you! Good night, and I have now made my simulation of a black hole. This is the first ever known image of a black hole made in P5.js. I need to blow my nose. All right, just because I don't have a lot of pixel space to work with right now, let's make the mass a tenth as large, and we can see there's my much smaller black hole. Okay, fine. Let's make it 1,000. Let me put on auto refresh, which will be nicer, and 5,000 and 3,000. All right, this is looking good to me. That's the size of the black hole that I want. Okay. Let's now draw the accretion disk. So let's make some sort of accretion disk. So I'm going to say ellipse. I'm actually going to I'm going to say no fill, stroke, and let's make it kind of grayish. And I'm going to draw the accretion disk as a circle. This .pos.x, this .pos.y, this .rs times oh. Breaking news. Okay, never mind. This just in from the chat. I forgot about this. I can use. I did not know. I forgot about this. I can say ellipse mode radius, which should now allow me to. Let me comment this out. Just use the radius as the ellipse. Perfect. Just use the radius value as the size of the circle. Thank you, Simon Tiger, for that great correction. All right. So now I'm going to say this circle is at the radius times 3, and maybe I will give it a stroke weight of 8. Ooh, and I want no stroke here. And let's make it a stroke weight of like 24 or 64. And let's give it some alpha. And there we go. All right, so that's kind of my visualization of the accretion disk. Now, the truth of the matter is this is not exactly correct, because I have a feeling that distance is right here in the center, whereas the stroke weight kind of fans out the thickness there. So it's a little bit off, and I probably should be a little bit more accurate about that. I guess what I could do is just add to the radius itself the half of the stroke weight. So if I add 32 there we go. I think that's accurate now. I mean, nothing about this is really accurate. All right, now let's draw the unstable photon orbit. So that would be at 1.5 of the radius. So I can do the same exact thing, but this time at 1.5. Maybe I want to make that one a little less thick. Give myself a little more space here. So that make this 16 and make this 32. And maybe this one should be like some kind of color, because I'm so good at design. Some kind of orangish. Ooh, I mean, that was better before, I guess. Some kind of orangish color. Okay. Look at this. We now have the black hole the accretion disk and a sort of photon orbit ray. Now the other thing that I want to do is I want to start a bunch of photons coming from, I'm going to try to like zoom into this here. I want to have them coming from over here towards the black hole. I need to know how far, I can't jump up because my green screen only goes this high. I want to know how far up does it need to be for it to not really curve, but travel in a straight line around the curved path of space and time to end up in an orbit, to either spiral out to infinity or end up into the black hole. So that we said was 2.6 Schwarzschild radius. Okay, so now what I'm going to do is I am going to create another class. I'm going to call this photon.js. Photon.js will be a photon. I'll make a constructor. This will also have a position. We'll give it an x and a y. And let's give it a little, let's make sure we include it in our HTML file. And let's also write a show function, which says, let's just make this stroke weight 4, point this.pos.x, this.pos.y, and stroke. Let's make this distinctly red just for right now. Actually, make it, yeah. All right. So now what I could do potentially is let me make an array, which could be, I'm going to call it light. Maybe I'll just call it photons, particles. Well, I'll call it particles, whatever. And I want to say for let y equal 320. Y is less than, and really this is height divided by 2. Y is less than, or y is greater than height divided by 2 minus, so I'm actually going to put these into variables so it'll make more sense. Let's say start is height divided by 2. End is height divided by 2 minus M87's Schwarzschild radius times 2.6. Height divided by 2. So y equals, actually I can start it at the end. And it's less than start. And y plus equal like every 10 pixels. So let's do that. Every 10 pixels. And what I want to do is say particles index I equals a new photon at where? X will be just width minus some amount, width minus like 20, comma y. What's wrong there? I is not defined. Particles, oh, okay. So I also need I'll just say particles.push. So I can add things to the array with the push function because I'm not using I to iterate. That makes more sense. And now here in the draw function, I can say for every photon of particles, p.show. So now there we go. I have all of my points of light that I want to send out at the speed of light towards the black hole and watch them follow their straight line path through the curved space-time thing. So now let me give them a velocity. So if I go back into my photon, whoops, I'm also going to say this dot velocity equals create vector traveling at the speed of light in the negative x direction, negative c, comma 0. Then I am going to do, whoops, not constructor, an update function, in which case this dot position dot add this dot velocity. And what I can do now is in sketch.js is I can say p.update. Ready? Here we go, everybody. There they go. Woohoo! All right, so what is the speed of light here? 30 pixels per frame. This is going to be going quite slowly, actually. Like the frame rate seems slow. 30 pixels per frame. That's not really a nice way to watch an animation. So I'm going to include another variable. I'm going to call it dt. This is the delta time step. So even though my animation frame goes one at a time, 30 frames per second, maybe I only want to travel ahead a little bit in time. So let's try 0.1, a tenth. And so all I need to do is what I need to adjust by that delta t is the photon's velocity. So I guess I'm going to make a copy of this. So I will just say this dot delta v equals this dot velocity dot copy, and then this dot delta. This is a little bit awkward about using p vector. Multiply by dt, and then I actually, not this dot. I just want a delta v, and then multiply that by dt, and then add that instead. So now I can see, there we go. There are the photons traveling at the speed of light, and then they go, but they're not curving, they're not changing. So now, okay. Break for a second. Okay. Now we just need to have them bend. We need to have them bend according to the curvature of space-time. This is now the moment where it makes sense for me to go read one of those papers and try to look at those formula. But I'm going to actually see what happens if I just apply Newtonian gravitational attraction. So I need this photon to basically have a force pointed in the direction of the center of the black hole that it accelerates its velocity towards it. So, but an interesting side note here, and this I guess is like an approximation of relativity, is since we can't go faster than the speed of light, it really only adjusting the direction. So that the speed is going to remain constant at the speed of light. Again, major caveats to how inaccurate this is, but it's a starting point. So, all right. So what I want to add a function. Basically, I want to be able to say I have some sort of force, which is m87. I like, curve, pull. I don't know what to say. I could say attract. I'm just going to say pull as a kind of arbitrary word. Pull that particle. And then I want to say particle, apply force, that force. So this is very similar to how I approach a very basic physics simulation in my Nature of Code example. So you could refer back to the chapters 1 and 2 of that book, which is essentially what I've got here. Now, so what I need is a function now in the black hole object called pull that expects a photon. And so what I need is, first thing I need to calculate this force vector is a vector that points from the particle itself towards the center of the black hole. So that's easy because I can take this position minus this position, and that gives me a vector. And that gives me a vector. That gives me a vector in the right direction. So I can say force equals p5 vector dot subtract this dot position minus photon dot position. Great. So now I want to normalize that force to give it unit of length 1. Then, I'm in the wrong camera. Thank you. Okay, thank goodness. So to make that vector, I'm going to make a variable called force. And I'm going to say p5 vector dot subtract. What is it? This dot position, the position of the black hole, minus photon dot position, the position of that particular photon. So that's the vector. Now, what I need to calculate the force of gravity according to the Newtonian laws of motion is that force of gravity equals the universal gravitational constant g times the mass of one object. Guess what? That's this times the mass of another object. Okay, what's the mass of this? Oh, we've got a problem now. So the mass of this is, well, 0. But the force isn't 0. So this makes kind of no sense. The good news for us is we're going to use this in acceleration. And because we also have force equals mass times acceleration, and I want to know the acceleration of this, acceleration equals force divided by mass. So this mass will just get divided out. Now, of course, I couldn't divide by 0. And this is the essence of why I'm kind of going down the wrong direction here to do this accurately. But it's a starting point. I can just consider this right now. The g times the mass of the black hole itself divided by r squared, or the distance between the photon and the black hole. R squared, or distance squared. So I have that value actually in my code because I have r is the magnitude of the force. Then I could just say force.set, then I could get I have r, which is the magnitude of the force. Then I could actually calculate that force magnitude, which is the force of gravity, equals, what did I say, g times this dot mass divided by r divided by r times r. And now I could say force dot set magnitude f of g, right? Photon. And then I can just say this dot velocity add force. Because what I want to do, photon dot velocity. Then I just want to add, that force to the photon's velocity. Okay. P dot apply force is not a function. So actually, I've simplified this. What I can just do is get rid of this whole extra step of returning the vector, and I can just do this. Whoa! Ah! Did you see those photons? So let's be able to see this a bit better, and we'll see why this is not correct. But first, let me do a couple things. One, let me say, let me make these variables, and let me draw lines. So let me say stroke 0, line from 0 start, 0 end, and width, 0 start, width start. And let me say stroke weight 1. And then let me also do the same for the end. I just want to be able to see where these are. So this is showing that spot. Now you can see it. Oh, and guess what? The speed of light, the photon should always be traveling at the speed of light. So I forgot about that. So this is a huge hack here. I'm going to say right here, when I do that pull, right in the black hole, I do that pull, I'm going to say photon.velocity dot set magnitude c. Dot velocity set magnitude. Or maybe I should just limit it. Let's just limit it. It could slow down, I suppose. It could slow down. Let's just limit it and see what happens. Oh, everything got sucked in. Look at that. The black hole sucked it all in. Okay, so a couple things. One is, so this is good. In other words, this is kind of a nice little simulation in the sense that the force is so strong, even in my very crude simulation, that it's never going to escape. Now, next up, let's add a little trail here. So the photon, I'm going to give it a variable called this.history. And I am going to, every time it updates its position, or every time before it updates its position, I'm going to say history.push this.pos.copy. And so then also this.history. Then also let's just say if this.history dot length is greater than, I don't know, 100. This dot history dot splice. Let's just remove the oldest element. And now I can say stroke 255, stroke 0, stroke weight 1, begin shape, end shape, no fill, for every vector in history, vertex v.x, type v.y. This dot history. So now we're able to see those paths as well as they. And so again, I don't have it right, and we can give ourselves a much longer history here, but I can at least, at a very minimum now, I can look and try to see where how this is working a bit more. I don't know why I just said that. You can edit that part out. All right, let me give the history a little bit more oomph to it. What I'm going to do here now also is I am going to start some particles from higher than end. So I'm going to say end divided, I'm just going to start all the way from 0, like the top. And then let's space them out by a little bit more. And here we go. And let's give myself a little bit more space to work with here, and see what we've got. Wow, nothing escaped. Look at that. Nothing escaped my black hole. Let's give it a smaller, again, it's not accurate. I've got this wrong because I'm not taking into account general relativity, which is kind of a thing. It's a thing. But I'm visualizing the idea here. Let's try, what happens if I make the gravitational pull constant smaller? Let's see if we can get anything to escape. Come on, rays of light, come back to the telescope. There we go. You can see it's there in the photon orbit. Oh, but back into the center. So we're getting the idea. Do we have something sort of similar to this? I think we do. Change the color to red. Try shrinking the mass. Okay, let's go back and change. You want the color to be red of the photons paths. So I can just take this out. Let's also make this stroke weight a little bit wider so I can see it. And then let me give myself here. Let me actually give myself much more space here. So I'm going to say window width, whatever space I have, window height. And let's also make this even less and see what happens. And then I'm going to do share. Let's do full screen. And here we go. Whoops. Oh, I have it hard-coded at 320. Hold on. One thing I need to fix. So what do I have hard-coded at 320? This. Height divided by 2. There we go. And let me go to full screen. Here we go. All right. Here is my black hole simulation. Rays of light, go! I think I need to move it over. This is bothering me. Sorry, everybody. Let's move it over so we can have a little bit more space to work with. 300. There we go. All right. Now, of course, you can see this should be where they're able to escape, but my simulation is completely off, so I should take out those start and end lines and just watch this go. There it is. The curvature of space and time. Center the black hole, please. Okay, that's actually not a bad idea. Center the black hole on the page. Okay, last thing. Let's center the black hole. That makes sense. And I'm also just going to, unfortunately, take out these lines, which are just because it really shows how incorrect it is. So for me to have some plausible deniability here. This is my new favorite phrase. Oops. Oh, what did I get wrong? Invalid or unexpected token. What did I do wrong? What did I just change? Huh? Line 13. Oh, whoops. Some sort of typo thing happened there. All right, let's look at this full screen now. And here we go. Let's see what we've got. Now it's running quite slow because of drawing all these trails. I think actually something that I could really do to make this, some things that I could do to make this better, a little faster, is, number one is in the photon itself, I could say, I don't have to add every single spot. I could just say like if frame count modulus 10 equals 0. That's going to improve the speed quite a bit. I also feel like, why am I only doing half? Maybe it's nice to do half. Let's just keep doing with half. Whoops. And now let me change this to full. Whoops. Let me change this to full. Oh, that's kind of funny. A little funny effect that I didn't mean. And there we go. Look at this. Look at that perfect orbit. Huh. That's kind of amazing that that happened. And there we are. I think this wraps this up. So there's a lot of flaws in what I've done. There's probably a lot more thoughtful ways that you could think about. First, designing this. First of all, it probably would look nicer. And one thing I kind of do want to change is just to draw the black hole last. Because then, at a minimum, at least it will look as if, because I'm drawing the rays behind that black circle now. Oh, I'm not. I must not have saved. And draw the black hole. I want to draw the black hole after, hit save. And then also, as I draw it, let's give a little alpha to this inner ring here. And then let me hit refresh. And we should see now, this should be a little bit more nicer to look at in the sense that it will look as if the photons are disappearing into the black hole because it's behind it. So there we go. And we've got a nice simulation of the idea of a black hole and rays of light curving according to space and time. Wildly inaccurate, very problematic. I can't wait to hear your comments about what I got right, what I got wrong, what kinds of ways I could improve this. The code for this is linked right here in the video's description. You can take a look at it and make your own version. Share it with me at thecodingtrain.com. There's a little way you can submit your own version of this challenge. And I will hopefully come back and do a follow-up video, either showing some of the ones that you have made, or make one that maybe tries to look at how the actual orbits equations work to simulate a more accurate version of them. I'm very tired after doing this for quite a long time. Thank you so much for watching. I appreciate it, and I'll see you soon. More photons. Why does everybody want more photons? All right. You asked for it. I will give you more photons. I mean, one thing I could do is just make a lot of random ones, but I don't think that'll look as nice. So well, I mean, I could make them every like 5 pixels. I was just worried about performance. So let me fix a couple things here. Oh, that's kind of nice looking. Let me fix a couple of things here. One thing that I want to do is in the photon class, I want to... Oh, I have an idea of how to make this much better. Oh, I got an idea. What time is it? 12 o'clock. Okay, I'm almost getting to the next segment very soon. But let me just do this, because this will be good. The things that I wanted to do are, number one is let's do this right here. So, oh, that's not going to help. Yeah, I don't love how that is, but that's fine. I'll just do it a little bit more often. And what I'm going to do is in pull, let's just say in pull, if r is less than this dot the event horizon, then photon dot stop, right? This is going to make things run much faster. Okay, hold on. Yeah. I don't think the photons are slowing down. I think I could make sure that they aren't, but I'm pretty sure that this will produce the same result, like photon dot velocity dot set mag c. Hold on, some people are telling me about the photons slowing down. I think this will be the same result. Oh, that is kind of a different result. Oh, they are. Okay, okay. This video is not over yet. Thanks to the chat, I think this is actually kind of problematic. The way that I'm doing this is the photons are actually slowing down, and they should stay. I shouldn't limit them to the speed of light. I should actually just keep their magnitude at the speed of light. Again, it's sort of inaccurate anyway, so what's the difference? I've also added more photons here, so you can look at it this way. So this is going to be a slightly different result. Because now I'm locking them at the speed of light. I think there's also a big performance improvement that I can make, which is that once they're sucked into the black hole, I don't need to keep tracking their position as well as, I don't need to keep tracking their position and keeping that history going. So I should really like shut them off as soon as they've been sucked in. So another thing that I can do here is, since I have that distance, I can say if r is less than the event horizon, I mean, I could remove the photon, just delete it, but I want to still see its path. So I think I'll say photon.stop. I mean, that doesn't mean anything, but I can then, in the photon class, I can have a variable called like stopped equals false. And then I can write a function called stop where I say this.stopped equals true. And then what I can do is, like, I don't want to continue updating it. As long as it's not stopped, I can just freeze its history. So I still want to draw it where it last was, but I can freeze its history. So with that, we now have, here we go. There's my photons flying at the black hole. Space-time starts to bend. The photons spin around, and some get sucked in, some curve, and there we go. Wonderful. All right, so what I've done here is a nice visual demonstration of this particular idea as explained in the Veritasium video. But as you know, using Newtonian physics and sort of classical mechanics here, there's a lot that's not accurate. So I would really love to hear from you. Number one, what did I get right? What did I get wrong? Give me your feedback about my kind of journey to try to learn about this stuff and create a diagram that looks somewhat like what was pictured in some of the explanations about how that image was made. Also, make your own version of this. Think about design, think about color, think about animation. I mean, you could certainly do this in 3D. And share that with me. You can go to thecodingtrain.com, link in the video's description to the actual page where you can submit your own version of this. The code will be right there as well that you can play with. Then, if you have ideas for how I might apply the formulas that I mentioned in some of these papers, here and here, which I will also link to make this actually behave more accurately, I would love to hear from you about that. Thank you so much for watching. I appreciate your willingness to indulge me with trying to do this, with making a lot of mistakes through it, sort of figuring out as I go, and I really appreciate it. Thanks so much, and I'll see you in the soon. Right, they're slowing down when they're going away from the black hole, of course. Of course they are. Yes, and they shouldn't. All right. So, black background, yeah. A second black hole, right? That would be cool. All right, I think I'm done with this right now. Yes, thank you. No, thank you, Jace, for keeping with me in the chat to get that correct. Whew. All right. Are you ready for segment 2? A little bit late here, but I think I have a lot of you watching. Stick with me. I'm coming soon to talk to you about NeuroEvolution and TensorFlow.js. But before I do that, let me just close this out. I want to tell you a little bit about Brilliant.org, the sponsor of today's Coding Train live stream. Amazingly. So if you like the kind of stuff that I do here, and you're looking for some ways to practice the ideas, outside even of coding, really, although what I'm going to show you is there are a lot of computer science lessons in there, courses and puzzles and daily challenges and discussions, you can visit Brilliant.org. And in fact, I have been trying it recently, and lots of members in our patron Slack group have been. A couple have been telling me they've been signing up and really enjoying it as a kind of companion to the stuff that I'm doing here. One thing that I want to just point out to you, if I go to the website and look at the daily challenges, this one right here is a challenge about relativity. Now my brain hurts a little bit from doing that whole black hole thing. So you might need to help me with answering this, but let's look at it. So by the way, relativity, and we're not talking here about special relativity, in terms of things moving at the speed of light, but the idea of relativity is as follows. You know, if you're sitting in a car or on a train that's moving fast and you have a bottle of water and a cup, you can pour that water into the cup because you're sitting still relative to the speed of the train. You and the train are moving at the same speed. The whole idea of relativity is how we observe motion from different perspectives relative to each other. So in a way, saying something is moving at a certain velocity isn't accurate. The only way to accurately say that is moving at a certain velocity relative to something else. After all, we're standing on the Earth that's spinning around its axis, and the Earth is spinning also around the sun itself. So, but like I said, I'm not a physicist, nor do I play one on YouTube. If you're interested in learning more about physics, and not just learning by reading textbooks or watching videos, but by practicing through quizzes and puzzles and social engagement, you can check out Brilliant.org. You should go, by the way, if you want to sign up right now, go to Brilliant.org/codingtrain to let them know that you came from here, and that helps me out a bit. Here you are. So look at this. A bouncy rubber ball is sitting on a T when it gets hit by a train moving to the right at speed v. After the collision, how fast will the ball move to the right according to an observer standing on the ground? Well, if it's a perfectly elastic or collision, right, wouldn't it just be v? I'm going to get this wrong. By the way, part of learning is getting it wrong. In fact, when I get it wrong, incorrect. It gives me a nice message. So let's see. 2v is the correct answer. So why is that the correct answer? Moving at the same speed as a train. To us, the train is still, and the ball is coming against the train with speed v. What happens when it crashes? It rebounds with the same speed, but the opposite direction, going away from the train. By the way, Joha, Pedro, Alfonso, please get in touch. Your answers are always at the top. Your answers are always at the top. People in the chat are talking about a typo, so I'm not sure what that means. But it rebounds at the same speed, the opposite direction, going away from the train. In the frame where the train is moving with speed v, that means a ball moving away with speed v plus v. The ball speed after is not exactly 2v, just like the train would not continue exactly speed v, because that would violate the momentum conservation law. But with the difference of the masses between the train and ball so big, the practical effect is the one described. Wonderful. Thank you for that excellent explanation. You can see how I thought about that incorrectly. But if you want to learn more about things like relativity and science, there's more there for you. Now, what I want to do is highlight something for you. And I didn't mention this, but if you go to brilliant.org/codingtrain right now, it's going to take you, whoops, let me just do that from here, brilliant.org/codingtrain. It is going to take you to the Stacks and Queues set of quizzes from the Computer Science Fundamentals course. So I can click here and look at all the courses, and you can see there's Computer Science Fundamentals and Computer Science Algorithms, which you can see are my recent ones, because those are the ones I've been going through. At some point, I'm definitely going to go through this artificial neural networks one, and maybe I'll refer to that as I do a lot of videos about that topic as well. And so if I click here on stacks, we can find this visualization and explanation of a stack. So give me a second to erase the whiteboard. And I am now going to do a little coding challenge, about stacks. And then you're going to be able to do those quizzes when I take a break. And I would love to hear from you how it went and if it made sense to you and if you got the answers right, that sort of thing. Okay. So there are many data structures and ways to store data and way to sort data and look through data in computer programming. And I cover those, I sort of weave through them in a lot of the different coding challenges that I do. Two data structures that are quite common are known as a stack. This is also known as first in, last out. Is that how you say it? The last thing in is the first thing out. No, last in, first out, right? I think that's how you say it. That's a stack. The idea of a stack is I'm piling things. So I might pile the letter B, then I pile the letter C, then I pile the letter Z, then I pile the letter A. That's adding things to the stack. They're stacking up. So that would be a push operation. Push is adding something to the stack. So if I were to say push K, right now we would push the letter K on top of the stack. The other operation, pop, is taking something off the stack. If I said pop right now, that would take K, remove it, and pop it off, and I would then have it in a variable, presumably. So value equals pop. So push is pushing a value, pop is popping a value. This is incredibly useful, and by the way, and it's used in a lot of scenarios where you need it. You've seen this before. You've seen it in P5, you've seen it in processing, push matrix, push style, pop style, or plain just push and pop. That's the way that matrix transformations are stored in a stack, because you want to save up, you want to build all of these different transformations, and you want to peel them backwards. And if you want to do that, push and pop is incredibly useful. A queue is a data structure that is just like a queue waiting in line. So you can think of it as like, okay, there's a little like ticket booth, tickets. Whoever gets in line first is the first one to buy the tickets. First in, first out. Is that how you say it? I forget what those terms are. Someone's going to tell me. No one has answered me whether it's first in, first out. Let me look that up. Actually, it probably explains it here. Yeah, there it is. Look, Brilliant's going to tell me. Last in, first out. LIFO. Thank you, Brilliant. Push. Last in, stack. Last in, first out. Okay, Q being the opposite, or the inverse, whereas the first one in is the first one out, because the first person to stand in line gets the tickets, right? So, of course, if I were doing this in a coding challenge right now and I needed a stack, I would probably just make an array. Because I can make an array, I can add things to the beginning, I can add things to the end, I can take things off the end. There's a lot of, arrays can serve as a way of storing data that could be a stack or a queue and manipulate it in all sorts of ways. But if I want sort of like computer science, bare bones way of doing this, the most efficient way where I just need exactly a stack and I never need to look at anything but the last thing that went in, I would basically use something that looks more like a linked list, which is I would have nodes, and I would have maybe a stack is the idea of a set of nodes that are connected to each other. And if I always add to the beginning and pull off of the beginning for push and pop, then there we go. That's my stack. Let's go implement that in code. Okay, I heard like some noise and the camera's going off. All right, so okay. So I am going to now wait, hold on, let me make sure I saved my black hole thing and close that. Let me close all this other stuff. 12:20, and here we are. Okay. All right. Here we are in the P5 web editor. I'm using the P5.js library, and I'm going to implement a stack in JavaScript. So I'm going to make a class called stack, and I'm also going to make a class called node. And the idea of the stack is it just has, I don't know, it has a first element. Maybe I'm going to say this dot first equals null. So when you first create a stack data structure, you just have basically this idea of a pointer pointing to nothing. So when I push to the stack, and sorry, I know you can't see that. It says stack. When I push to the stack, I'm going to add the first element there. So the idea is that I might have a function in the stack called push with some value. And what I'm going to do is I'm going to create a new node with that value. And then if this dot first equals null, then this dot first equals that node. So this is the code so far for putting in a first node, This is the code so far for pushing an element into the stack when it's empty. So in order for that to work, I need to now have a node class. So I'm going to have a node class is just a thing that has, what does it have? It has a value, right? That's the thing that's being stored in the stack itself. This could be an object, could be a letter, could be a number. Maybe I'll just use characters like I did in my diagram over there. And then, most importantly, a node, right? If I push that first node in here, the node has this empty little pointer that's pointing that also to null, because I need to just keep having these things point to each other. So what I would then do is I would say, then I would say this dot next, I can call it next, like where it's pointing to, is null. So this would work to push something in. So I should be able to say, let's get rid of the draw. I don't need the draw loop here, right now at least. Let stack equal a new stack. Stack dot push the letter A. So let's push the letter A. Now what if I were to say stack dot push the letter B? And the fact that these are in alphabetical order is irrelevant. I should probably pick letters that aren't, which I will do right now just to make it, there's no it doesn't matter what the letters are. They're not, it's not going to be in sorted order, alphabetically or numerically. The whole point of the order is it's the order that I'm putting things in. So if I now push the next one in, what do I need to do? Well, you would kind of think like, oh, put it here, right? Because that's the empty spot. But actually, I don't want to do that because I want to keep a pointer. If I'm going to pop, I always want to get the latest one off. So actually, what I'm going to do, where's my eraser? And I'm going to fix, first I'm going to fix the fact so that you can see the word stack here. Because stack is actually, this is actually first. That's what it is. This first is pointing to this, which has the value m in it, right? So first has the value m in it, and is pointing to null. So now I want to push B. So what I actually want to do is I want to create a node with B in it. I want to have B point to M as its next node. And then I want to have first point to it. So I basically want to insert it in between first and the latest thing. And another thing would come and point to B, and then first would point to that. So I always have this first pointer to the latest thing. So how would I do that? Let's see. So if it's not null, then what I want to do is say, what did I say? N.next equals this dot first, right? I want to point the thing that I'm putting in right into what was first. And then what do I want to do? I want to say this dot first equals n. There we go, that's it. So now I have the functions push, and I have the function, I know I don't, but let's make the function pop. So now what I'm going to do in pop, well, I should probably test this to make sure it's working, but let's not do that just yet. Well, I'm going to use pop as a way of testing it, because if I push things in the right order and pop things in the right order, then it should work. And I'm going to use the brilliant quiz to sort of figure that out. All right, pop. What do I want to do? So, oh, this is easy. I just want to return. Oh, well, actually, I need to do a couple things. What do I want to do? When I pop something, I actually get rid of it. So popping is the process of, oh, you can't see this one. I've really gone off. Let me make a new diagram for you. Over here. All right. I'm making a new diagram to illustrate the push and pop process better. So what I have here is I have this, when I create, when I first create the stack, I have a pointer or a variable name called first, which is pointing to nothing. Then if I want to say push a value like m, then I want to make a new node called m, and I want first to point to it. Then if I'm going to say push b and push x, then what I would do when I push b is I make a new node called b, point that to m, and then first, I change first to pointing to b. Then when I push x, I make a new node called x, I point it to b because I have that, and then I have first point over here. So what do I want to do if I want to pop? If I want to pop, what I want to do is just take the value x, right? Take the value x, return it, return basically first's value. And then what I want to do, but I'm going to have to do this in a different order because I can't, once I return, I'm out of the function, but this is the idea. I want to grab this value and then I want first to point to first.next, right? Because once this is popped up, then this pointer is what first points to, and this is gone. Now, if I were in some programming language where I had to do memory management, I would have to release the memory for this, but I'm in JavaScript. It's fine. It'll be garbage collected. Okay, so let's try doing pop. So I want the value to be first dot, and what is it in the node? Value? Then I want first dot, first to equal, this dot first. And then I want this dot first, first is null, to equal this dot first dot next. I think that's right. So first get the value, then point it to the next one, and then return that value. Okay? So there we go. So now, if I were to do this, mb x, and then I'm going to say console log stack.pop. We are now going to find out if I did this correctly, if my code is correct. mbx pop off x, pop off b, pop off m. Sorry, I'm just looking at the chat for a second. It's kind of interesting what people are saying. So it looks like things are working correctly. Now, let's make our test a little bit more sophisticated to see if it really is working correctly. So I'm going to go back to this, this quiz on stacks. And there's some wonderful explanation here that's going through with some nice animations. It's basically going through exactly what I just talked about. And now we're going to get to our first question. So this is, and it's using numbers. So this sequence I should be able to implement now with my stack. So I'm actually just going to copy paste this. And I'm going to put it into my code like this. And what I'm going to do is I'm going to say stack.push. So I'm going to add my object name here for all of these. And then what I want to do is console, I guess what the quiz is asking me to say, if I go back here, what the quiz is asking me to say is, what will the stack look like after the operations are applied? So what does the stack look like? So I should probably add a function here to call like traverse or examine. And what that will do is I will start with while. So I'm going to say let node equal first, while node is not equal to null, console log node.value, and then node equals node.next. So this is like a loop to go from node to node. Start with the first node, spit out its value, go to the next one. Okay. So in theory, if I say stack.traverse, and I'm not going to do it yet, I'm going to comment it out. I'm going to comment this out, and I'm going to run it. So I don't get any errors. Oh, pop was called without a matching push. Oh, I must have an error. Fascinating. All right, this is interesting. I mean, this can happen. Oh, no. I forgot. Oh, I have a big problem here. So pop, this is one of the flaws sometimes of working with P5 is that P5 is a beginner-friendly environment where there's lots of stuff in the global namespace. So this has to be stack.pop, of course. So I'm glad I tested that in stack.pop because there is actually a function called pop. It's popping off the transformation state, the styles, that kind of thing. But that's not what I'm doing here. So there's nothing about this that I need P5 for, although I could diagram the stack. All right, so no more errors, so that's good. Let's look at the quiz. So let's try to answer this. You think about this for yourself for a moment. I'm going to go over to the whiteboard, and I'm going to figure out the answer myself. So hopefully you have the quiz up, maybe on a different screen, so you can see. So it's push 7. So push, I'll just write it here. Push 7, push 8, pop, push, I guess I don't need to write it out, but why not? Pop times 3 and push 40 and then push pop divided by 2. Okay, let's do this quiz. So here's my stack. First thing I'm going to do is push 7. Then I'm going to push 8. Some of you can probably do this in your head, but I'm going to diagram it out. I always find that to be helpful. Then I'm going to pop. So I pop off 8. Then I'm going to push, I'm going to pop 7, multiply it by 3, so it's gone, and push that back on. 7 times 3, 21. Then I'm going to push 40. So I push 40. Then I'm going to push, then I'm pop that off, divide by 2, I get 20, and push it back. Then I have this. So this should be the state of the stack. 21, 20. In my other way of looking at it, it would be this, with this being first. So let's look at the quiz. Let's see if I can get it right this time. 2120, hit submit. Hey, I got this correct. Okay, I got it correct. Now the question is, will my code get it correct? So now if I add this stack.traverse, first is not defined. It's line 38. That must be down here. I always have this trouble. This dot first. Okay, there we go. Let's try this again. 20, 21. Now, is that right? Is the order right? So I think it is right, but just because of the way I'm traversing it. But let's say, right? Oh yeah, it is. Because 20 is what would pop off first. So if I console log stack.pop and console log stack.pop, 2021, 2021. Okay, so that is the correct order. So now you have seen me implement a stack. I will leave it to you as a challenge to maybe visualize and animate this. So what if you're adding things to the stack and you're actually seeing them pile up? You can use P5 Canvas to draw them. When you're popping things, you see them pop off. There could be a nice way to make an animated version of this. But you can also now, I would be curious here, I'm going to take a 5-minute break. Please go to brilliant.org/codingtrain. That will take you directly to this quiz page. While I'm taking a short break, if you wouldn't, you can go through and try to answer some of these quiz questions. You can go through the stacks, then you could go through the queues. And when I come back after, I'm going to get some water, wash my hands, which are full of whiteboard marker stuff. I'm going to come back and, oh yeah, sorry, this is very, I'm sorry, before this is what's wrong. Everything was right. This is right. The route was right. This 20 first points here. Sorry. This is very important. That's wrong. Come back and I will be here. I'm going to spend a little bit of time talking about NeuroEvolution and TensorFlow.js. So thank you so much for Brilliant.org to the sponsorship. If you have a minute today to sign up for free at Brilliant.org/codingtrain. Also, the first 200 people to sign up for the premium subscription, which unlocks all of the courses on Brilliant, will get 20% off from that link. So thanks very much. I will be back in just a short bit, and enjoy your stacks and queues quiz. Let me know how it goes, and I look forward to hearing about it.
As always, I always forget the this dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot, this dot song. This dot, this dot, this dot. Never forget this dot, this dot, this dot, this dot, this dot song. This dot, this dot. This dot, never forget this dot. This dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot, this dot song. This dot, this dot, this dot. Never forget this dot. This dot, this dot, this dot. Never forget this dot. I'm gonna do the this dot, this dot, this dot, this dot, the this dot song. Never forget the this dot.
Unicorns and rainbows and cupcakes. What else is there? Yes, kittens. Thank you very much. Kittens and rainbows and cupcakes. Notice that. Look what I get. I'm really losing my mind. Okay, let's do it. Kittens and kittens and kittens, kittens and kittens and kittens and kittens, kittens and kittens and kittens and kittens, kittens and kittens and kittens and kittens and kittens, kittens and kittens and kittens, kittens and kittens and kittens, kittens and 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 kittens and kittens and kittens. Kittens and kittens and kittens and kittens, 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 kittens and kittens and kittens and kittens. I feel just sort of like a nice feeling of relaxation. Everything's going to be okay today. Dream is not broken. It has not frozen. This is a wonderful thing. Okay, we're going to do it. I'm really getting to something. I need my sound effect. Unicorns and rainbows and cupcakes. What else is there? Unicorns and rainbows and cupcakes. That was invalid syntax. I forgot. There was one other thing here that I think is important that I will use continuously over and over again in all sorts of text generation analysis things that I will use continuously over and over again. First thing I need to do is, yes, kittens. Kittens, kittens. I'm really losing my mind. Okay, we're gonna do it. Kittens and kittens and kittens and kittens, 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 kittens and kittens and kittens and Das Vidania.
Hello, I'm back. I don't know if you've heard that particular remix of Unicorn, what's it called? Kittens? I don't know what it's called. There's a whole playlist on SoundCloud of Coding Train remixes. There's one there's one actually that I don't know that I have over here that I really love. I need to kind of redo my soundboard. If you're like making those kind of remixes, they bring me such happiness and joy. I love to play them, listen to them. I even want to like learn them on the ukulele. Then there are these weird like MIDI instrumental versions of them, so that's it. So Simon was just telling me in the chat that if you keep going, I'm going to scroll up to this message, that there's a fun, that there's, if you keep going with this quiz, there's other operations on stacks that it asks about, and that they're really fun to do. So I hope that you have a chance to check out Brilliant and practice some of these concepts that I'm doing in my videos on their website as well. Thank you so much to Brilliant.org for the opportunity and the sponsorship of the Coding Train. If you have any questions or run into any issues, you can post them there. You can send me a message, leave a comment in the video, and I'd love to try to help you out. All right, so the next thing that I want to do here, is talk about neuroevolution, and talk about neuroevolution with TensorFlow.js. Sorry, my brain is starting to shut off. And I've got about a half an hour or so to do this, so I have an idea of how I'm going to work on this. First, let me just do this stack.js example. So I'm saving this, and I will put a link to this stack code in the video's description. If somebody who's a mod right now in the chat wants to sort of post a link to this sketch URL, then you can access it right now. OK. So let me get these cameras. You'd think that when I took my 5 or 10 minute break that I would remember to cycle the cameras, but hard. Oh yeah, and peek. So people are talking about that peek. So peek is the peek function instead of pop and push is an additional function in a stack data structure. So I would say try implementing that. I didn't implement peek. You could implement it and let me know how that goes. And you're going to need to implement it if you want to answer the rest of the questions on Brilliant through your code example. OK, so I'm over here for a second to erase this. So let's see. So I'm erasing the whiteboard in case I need it. I'm closing this out. And what I'm going to do is I'm going to go to thecodingtrain.com. I'm going to go to Coding Challenges. I'm going to look for, by the way, if you missed last week's live stream, Rubik's Cube Part 3 will be coming out tomorrow. Mathieu and I have been sort of like editing it together. The content is already online in the live stream, but the Part 3 edited down to about 25 minutes, which has the animated turns. I haven't tried applying a genetic algorithm or a neural network in some sort of machine learning way to solve it. I thought I would take a break from the Rubik's Cube today, but I will try to come back to that. OK, so I'm looking for NeuroEvolution. Flappy Bird Part 5. So improve saving and loading brain model. Let's see, let's go to here. Let's look at download the code. I don't remember which example I'm getting right now. So let me grab the code for this. This is not the GA one, so I actually need to go back, which is fine. Let's go back to part 4 maybe, and then do download the code. Let's see if it's this one. Yes, this is it. So I'm gonna change this to Flappy TF.js. Sure, and then I'm gonna put this on the desktop. So if you want to follow along, I'm starting from the code base from this particular video. And so, oops, I'm on the desktop. Here it is. Then what I want to do is open up iTerm and go to the desktop and go to this, and open this up in Visual Studio Code. Let's just go here. Great. We can. Let me do that to all of these. And, oh, I actually have the save functionality built into it. Interesting. Okay, so that I might need to take out. But I'm going to leave everything as it is. Okay, then I need to run a server. And get the console going here. And then I need, what else do I need? I need this. This can go away. Then I need a TensorFlow.js. And where's like the quick start? See tutorials, see the guide, see demos, get started, get set up. This is what I'm looking for. Great. Actually, the newest version I think is 1.0.4. So I'll do this. Okay. And let's just also go to, because what I would like to do here is do this. And speed this up a little bit. Okay, that's a little bit too much. Okay, so I am ready to begin. Let me just make sure the code is visible. Yep, that's fine. Turn this off, and I'm ready. So in a way, this could be a new coding challenge. It could just be like a supplemental video as part of my NeuroEvolution series. It could be part 6 of the earlier coding challenge. Yeah, maybe I'll just do that. It's sort of weird, but maybe it makes sense to make this like part 6. I'm not sure. Tricky. I don't know what to do, but we can always fix that later. All right, let me cycle the cameras, and we're going to get started. This probably is going to take more than half an hour, but let's see. Okay. Oh. Okay. Simon is pointing out that, again, he's been reminding me about this, and it is true that Coding Challenge 144 in base 12 is actually 100. So since I didn't celebrate Coding Challenge 100, I could celebrate 144, and I could do something about base 12, but I just couldn't come up with an idea. So I think that the black hole to me is special. So in a way, that will be Coding Challenge 144, and it will be celebrating in base 12, 100. Okay. All right. Let me just check one thing on the channel, torturing you all. Let me just check this, like, NeuroEvolution. Like, am I making, well, doesn't really matter. It's going to go in this playlist, but c'est la vie. Okay. All right. I probably should find, there's probably a version of this that has the nice design in it, but that's okay. Okay. I think I won't say coding challenge because I will, oh, hello, Graven Development. Thank you so much for your for your donation. That is really kind of you. I certainly appreciate it. Okay. All right. What am I doing? All right. Hello, welcome to another Coding Train video about neuroevolution, the process of evolving an optimal neural network for some type of scenario, like playing the game Flappy Bird, or kind of crude version of the game Flappy Bird. Hello and welcome to another Coding Train video about neuroevolution, which is a term that describes, the sort of scientific term for this are NEAT, neuroevolve, never mind about the NEAT thing. Développement. Hello and welcome to another Coding Train video about neuroevolution. So this video, what I'm going to do is I'm going to take my previous sort of finished version of neuroevolution, the process of evolving the optimal weights of a neural network to perform some kind of machine learning task. In this case, I'm making a guess based on the environment of this very crude Flappy Bird game. I'm not making this. The neural network is making a guess whether it should jump or not. And so this is a very simple, actually, scenario to solve. And so it's a nice demonstration of the idea. And I've been meaning to return to this topic for quite a while so I can try to look at some more complex scenarios. So neuroevolution can be applied to a lot of problems that different reinforcement learning algorithms are also applied to, but it's a pretty different technique. And so there's like 5 or 6 or 7 videos all about neuroevolution that I would recommend you check out, or you can start right here, because what I'm going to do in this video is I am going to take the existing version that I made, which used a toy neural network JavaScript library that I implemented in yet another video series to kind of learn more about neural networks and spin up a very, very basic one in JavaScript without other dependencies. But I'm going to replace that now with TensorFlow.js. And I think this is better because I will be able to build better, more robust projects without having to be responsible for the sort of underlying machine learning framework. I can rely on TensorFlow.js to give me all of the sort of possible configurations of a neural network that I can then use in my own system, my own evolutionary system. Now, I should say, what was I going to say? There's something that I just thought of a second ago. There was something important. Oh, thank you there's a new member. It's going to come back to me what I was saying. Matt's team, thank you so much. If you sign up to be a new member and you're looking for your invitation to our members Slack channel, go back to the community tab. This is all a message just for Matt's, by the way. Go into the channel's community tab, and there's some posts there that are members only that we'll explain. Okay, wait. Yeah, the collision detection is not pixel perfect. Wait, I was saying something. I don't remember. There was something I was going to say. All right, that's fine. Cut. Okay. I just have to keep going. So what you're seeing here is the last example from part 5 where I saved a trained model and am loading it into a version of the game and watching it play out. What I did previous to that is what you're seeing right here, which is this is launching 500 random neural networks to try to make guesses. I can use this slider to sort of speed up the system, and over time, those neural networks are going to perform the processes of crossover and mutation. It's not actually doing crossover, it's doing crossover, which would be the act of combining 2 agents' genetic material together into one. I'm just taking one and copying it, but then I am mutating it to optimally search for the configuration of weights that will work the best. And just to remind you, when am I talking about the weights? Just to remind you, when I'm talking about the weights, this is what I'm talking about. So we have the Flappy Bird game. This is the agent that needs to make a decision. In a way, it's a classification problem. Should I go up or should I not go up, right? These are the only two possibilities, a very simple classification problem, two categories. I am the human being, have basically done the feature extraction. I could use the environment, the input to the neural network, as this image, like all the pixels of the game. That would be a wonderful thing to try, and I would love to do that, especially once I have convolutional layers with TensorFlow.js, which is not something I have in my toy neural network library. You might not know what a convolutional layer is. Don't worry. If I use it, I will explain it. But I have done that feature extraction. So I have decided that the features that I want to use as inputs into my neural network are, I think it was like the bird Y position, the bird like Y velocity, the top pipe location, the bottom pipe location, and then I'll call this like X, the distance to the nearest pipe. So these are what I've decided are the important values to use from this game to feed into the neural network. So that means the neural network has 1, 2, 3, 4, 5 inputs. These all get normalized into a value with a range between 0 and 1 and fed into the neural network. Then the outputs is a classification problem, so there are just two outputs, and they would each output a number. If I got something like 0.8 here and 0.2 here, that means there's an 80%, basically 80% probability confidence score that I should jump, so I will jump. Now I could actually pick random numbers and that kind of thing, but I'm just going to take the highest one, the argmax, so to speak, and go. So neural networks are able to learn a sophisticated amount of information through hidden layers. So the inputs don't pass directly to the outputs, but the inputs pass through a hidden layer. And I don't recall what I picked as the configuration of the hidden layer, but I think it was something like 8. So if there were 8, I think that's what it is. We'll look. 1, 2, 3, 4, 5, 6, 7, 8. These are what are known as dense layers, meaning every single node is connected to every node. I will not sit here and draw all of them, but I will start that process. And then all of these, are connected to the outputs like this. So a neural network's core data, the configuration of that data is in a matrix, because every one of these connections has a weight. So if there are 5 here and 8 here, that is 40 weights. If there are 8 here and 2 here, that's 16 weights. Now the truth of the matter is there's also a bias. So there's a bias for each one of these and a bias for each one of these. So the configuration is all of the weights, all of the biases for each of these nodes. But these are the details that I cover a lot more in the series about building a neural network from scratch in JavaScript. So if you want to learn about that, you can go back. What all you need to know for here is that I have a way of creating this neural network. I have a way of feeding these values into it and looking at the stuff that comes out. So let's go look at that code. So if I go look at the code, we can see that here. There's this idea of a bird object. And the bird object makes a neural network with 5 inputs, 8 hidden nodes, and 2 outputs. I don't know what I've said here, but this is known as a feed-forward neural network. Multi-layered perceptron, it's 2 layers. The inputs, it looks like a layer, but these are just numbers coming in. There's a hidden layer and an output layer. That's an important terminology. So that's happening here, and you can see in the bird sort of like takes all of those properties, its y position, the closest pipe's x position, its velocity, makes that into an array, feeds that into a predict function, and then I just sort of like, if the first output is greater than the second output, jump. So this is that process. And all of this happens in this neural network library. So there's neural network.js and matrix.js. This is like if TensorFlow.js was made by one person who really didn't know what they were doing. That's what's in here. So what I want to do is I am going to delete this folder. Right? I'm deleting it. It's gone. Gone. Move to trash. Boom. So now when I go over here and I hit refresh, of course it doesn't work because we have no neural network.js. Can I get this, I don't have a watch on, however long I have right now in the course of this video, working again without my library, but with TensorFlow.js instead? That's the thought experiment here. So in order to do this, actually, though, ironically, I think what I want to do, a couple things I need to do. Whoa, what's this ridiculous-looking HTML file that I have? Sorry, everybody, hold on a sec. Let me just clean this up a little bit. This can come out. There we go, that's better. And just do this. So the header should have all these script tags. Oops. Stop. Should have the P5 libraries. This should be NeuroEvolution with TF.js. Recent P5 is 8.0. And this would be in the body. Shouldn't have like bird there also. I must have lost that by accident. Bird and pipe too, right? Bird, pipe. Okay. Same thing. So here's my HTML file, and you can see that it has the P5 libraries. It's loading my neural network library, and then these are all the files for the Flappy Bird game itself, as well as a file that includes some information about how the genetic algorithm works. So what I want to do, I need to take these out, and then I want to import TensorFlow.js. So I have the TensorFlow.js website up, and this is the script tag for importing TensorFlow.js. So I'm going to add that here. And actually, I'm pretty sure that the most current version is 1.0.4. So let's add that. And now I'm going to go back here and hit refresh. Now, of course, neural network is not defined. So we've got fewer error messages here now, which is good. I just want to make sure TF is loaded. So like, for example, I can call TF memory, and there's no memory being used. But I can see that TF.js is loaded because I can call TF functions in the console now, which I'm going to need to do to figure all this out. All right, so now I think the thing that I want to do is I don't need to do this, but I think it would be nice for me to create, I'm going to create a file called nn.js, and I'm going to make a little wrapper for a neural network. And actually, one of the reasons why I want to do this, sorry. Sometimes things go haywire. One of the reasons why I want to do this is, as you know, I've made a lot of videos using a library called ML5, which is a wrapper around TensorFlow.js, which allows you to work with some of the machine learning algorithms without having to manipulate the lower level details of TensorFlow.js. And so this is kind of a little bit of maybe a preview of that, because this idea of neuroevolution is something that I would like to work on putting into the ML5 library. So if I make a neural network class and I write a constructor, we know here that in the bird object, what it's doing is it's making a neural network with 5 inputs, 8 hidden nodes, and 2 outputs. So there's no reason why I can't actually just keep that same structure. And I'm going to have 3 arguments. I'm just going to call them A, B, and C, because at some point I might need to call the constructor in different ways. And I'm going to then say this dot input nodes equals A. This dot hidden nodes equals B, and this dot output nodes equals C. Then I'm going to put, by the way, I did this in a class that I'm teaching last week, so I kind of have quite a bit of a sense of the plan here. So I'm also going to write a function called this dot create model, because I might need to do that in different places, and then I'm going to make a separate function called create model. So this now is the function where I want to create my neural network using TensorFlow.js, and I'm going to use the layers API. The truth of the matter is this particular architecture, right? This is perhaps one of the simplest, most basic, vanilla, so to speak, neural network architectures. It's got 2 layers, 1 hidden layer, very few nodes. There's no convolutions, no fancy stuff, just the very basics. So I could probably do this with just simple TensorFlow operations itself, but I'm going to use something called tf.layers, which is actually based on Keras, which is a Python library for TensorFlow in Python. So many things. I've talked about these in videos. But basically, tf.layers is an API that allows me to create a model from a slightly higher level perspective. So one of the key functions in tf layers, and I'm going to create a variable called model, is tf.sequential. So if I say tf.sequential, that should create for me a sequential model. And we can just take a look at that here in the console and see, there we go. It made something that works. You can see there's all these parameters. Is it training? Now, interestingly enough, what I'm doing in this video is not really what TensorFlow.js is designed for. Almost everything in TensorFlow.js has to do with optimization functions and algorithms for learning and tweaking weights and back propagation. I'm not doing any of that. This NeuroEvolution thing is quirky and weird. All I actually need is a bunch of neural networks and the ability to feed data through them, and then I can just delete and add and mix them up. So actually, most of this stuff will not get used. But what I want to create then is my first layer. So the first layer I'm going to call hidden. So I'm going to say const hidden equals tf, I think it's dense. So I think I better look up the documentation at this point. I certainly don't have this stuff memorized. So I'm going to go to the API, and I'm going to go, oh boy, there's many more revisions since I think 0.04. But I'm going to go here and I'm going to look for dense. So I want TF layers. Oh, I'm in TensorFlow.org. Wrong API. I want the TensorFlow.js API. I clicked on the wrong place. Those were the version numbers for the current TensorFlow, not TensorFlow.js. So I want to go to dense, TF layers dense. So this is what I'm looking to do. And I can see a nice little example of it here. So I'm going to create a TF layers dense. dot layers dot dense. And then I need a little object which is going to contain all of the configuration information for that dense layer. And what are some things I can configure? I can give it the number of units. That's my hidden nodes, which is the hidden nodes. I also want to tell it how many things are coming in, like what is the input shape. So this is the layer. I need to tell it about the input shape. I forget what that's called. Somewhere in here I'll find input dim, which would be the input dimensions, I guess, which would be this dot input nodes. I'm forgetting my this dots, as always. As always, I always forget. So there we go. What else do I need? I think an activation function I definitely need. So activation. Activation. Now this merits quite a bit of discussion. An activation function is how the data gets processed as it's fed forward. So all of these inputs, the numbers that are these values, come in here. They get multiplied by those weight values, summed together, and passed through an activation function. The activation function's job is basically to squash the values, to sort of enforce nonlinearity, to allow for the stuff to go to the next layer. And there are all sorts of reasons why you might pick one or the other. And there's more recent research, and it's changed over the years. And I've talked about this in other videos. I'm going to pick sigmoid as a kind of default activation function that squashes all values between 0 and 1. And I'll include some links about sigmoid in the video's description if you're curious. So I forget exactly what I do here, but I think I can just write sigmoid as a string. And somewhere in the documentation there is a list of all the activation functions. Do I need anything else? I think that's good. So then I just want to say this.model.addLayer maybe? So TF sequential is what I'm doing here, which would be here. And input shape is probably what I want, not input dimensions. We'll see. I'm noticing that there's input shape. So actually, I think that's what I want. I mean, that's certainly what I used previously. So input shape, and it would be just that number of nodes, but inside an array. A shape is a way of defining the dimensionality of data. So if it's just a list of stuff, like a list of numbers, it's an array with 5 things in it. So that's how I define a shape. So then I would say model.add. So this.model.add the hidden layer. Now,
I want to make an output layer, which is going to be TF layers, also dense. And I want to, what do I want? The units is this dot output nodes. And then I actually do not have to define the input shape for this layer because it can be inferred from the previous one. So I couldn't infer the number of inputs from the hidden, because hidden is first. But the last layer here, these outputs, I know that I just added this layer. If it's dense, this is the shape of the input. So all I need to do is that. And then I also need an activation function. And I'm gonna make it softmax. So softmax is an activation function which like sigmoid, squashes all the values to a range between 0 and 1, but it does something even more. It basically enforces that all those values also add up to 1. It basically turns them into probability or confidence scores, and all of them add up to 100% or 1.0. And there's more to it than that. It's kind of in terms of how the mathematics have worked, but that's the basic gist of it, and that's what I want. I want the probability of whether I should jump or not jump. So now I should be able to say this dot model dot add output. And then if I go back to the documentation, I don't need to do this fit stuff, but let's call, do I need to compile it? So interestingly enough, usually you need to compile. You need to give a loss function. Traditional machine learning, you're going to have a loss function, an optimization function. You're going to train it with data. I'm not doing any of that in NeuroEvolution. Remember, if you've watched my other videos on NeuroEvolution, I'm doing this weird thing. I just need a random neural network. That's all I need. So I don't know if I need that compile step, but I'm guessing I kind of do. So I'm going to say this dot compile, but I'm just going to give it an empty object because I don't care about those other things. So let's this dot model dot compile. So now that I have that, I should be able to, with my code, I'm probably getting a little bit further. Like, look at that. Cannot read property minimize of undefined. Oh, because I didn't give it any optimization. Let's get rid of the compile. Let's see if I can get this to work without this dot model dot compile. Maybe compile only has to do with the learning process that I'm not using. Great. This dot brain dot predict is not a function. So now I have the next thing that I need to implement. So where is that? That's in bird.js. And what is it saying? So I'm able to make the neural network, and then I am calling predict, and I'm giving it an array. Perfect. So what I need to do now in my class here is I'm going to write a function called predict, which will receive an array. Now, what I would essentially be doing is now calling this dot model dot predict with that array. Only here's the complexity of using TensorFlow.js. TensorFlow doesn't work with traditional JavaScript arrays. It works with something called tensors, which are multi-dimensional arrays that they're multi-dimensional things, collections of numbers that are living in the GPU's memory. That's for optimization purposes. The operations can happen faster on the GPU, which is optimized for a lot of matrix math. I don't really need that optimization, to be clear, because I'm working with the tiniest thing here, but I still need to convert this stuff to tensor. So I'm going to need to say the x's, I'm going to call this, the inputs are often referred to as x's, equals tf.tensor. And what do I have? What's the shape of my array? It's one-dimensional, right? It's just an array. But the thing is, what TensorFlow.js expects, so this is like my data. It comes in as an array of numbers, 1, 2, 3, 4, 5, right? All of this stuff, 1, 2, 3, that's only 4, but whatever, you get the idea. There's another one there. The thing is, TensorFlow.js is kind of thinks like, you would never be so crazy as to give me just one thing. Usually you're going to give me like 1,000 rows or data samples. So it's actually looking for a shape that is like this, that would have a bunch of these. So I just need to take my inputs and put them in a 2D tensor, because it's an array of arrays. So if I do that, tensor 2D x's, I think that's all I need to do. Then I need to call predict with the x's. Now, that's happening synchronously. I need to get the data off of, oh, and this would be y's, sorry. The y's would be the result of feeding it forward. So that's exactly this process. Predict is the function to feed this stuff forward, and now I have the y's.
I'm going to do something which is a little bit ill-advised. I want to be able to look at those values. So right now, the y's are a tensor, and that's living on the GPU. In order for me to pull it off the GPU to use it, I need to call a function called data, which is getting the actual data, and that's something that happens asynchronously. So I need to deal with a promise or a callback, but because I'm working with such tiny bits of data here, it's going to be much simpler for me right now, at least to get this working, to just say, basically, the outputs equal y's data sync. So the data sync function gives me those outputs. Let's console log them. And let's say return outputs also, just so we see what's going on here. So I'm now going to run this. Neural network.predict at bird.think is not defined. What did I miss? Predict, neural network predict. Where am I? Bird, line 54. This.brain.predict. What did I miss? Oh, x's is not defined. Sorry. The error is x's is not defined. That's weird. Neural network.js 10. Array, x's. Oh! Sorry. Sorry, there's a major error in here that you probably all noticed, but I didn't. I'm taking that array and converting it to a tensor. So ARR is the array, and maybe it would make sense for me to call these inputs. I'm taking the inputs as a raw array, converting them into a tensor, passing them through the model, pulling out the outputs, and returning it. OK, let's see how that goes. Tensor 2D requires shape to be provided when values are flat. Oh, guess what? This has to be inside an array, right? Because the whole point is it wants the 2D thing, so it wants that array inside of an array. OK? So that, oops, TikTok. So that, OK, stop. So that should fix that. Great. Oh, look, I'm getting stuff. I'm getting things. Why aren't I seeing anything? Oh, look how slow it is. It's so slow. So this is sort of like the weird irony of all of this. So this is really the irony here. I am doing a ton of operations that are copying and removing data from the GPU. I really should be doing all of them at once, right? There's no reason why I couldn't pass all. Oh no, I can't do that. I have different models. Never mind. Let me just go back. So this is kind of ironic in a sense. Like I'm using a much more powerful JavaScript engine for deep learning that does all the operations on the GPU with WebGL to optimize it, and yet it runs super slow. This is really because I'm a crazy person and kind of doing this in a weird way that TensorFlow.js is not really designed for, where I'm like have all of these different models and I'm copying the data with data sync. So there's a couple things I could do. Number one is let's just, for now, and I'll have to come back to this or think about how to make this run faster or be more thoughtful and maybe do this stuff asynchronously. But what I'm going to do right now is I am going to just reduce the number of birds to half. And I'm also going to do something a little bit silly, which I'm going to in setup, I'm going to say tf set backend CPU. Because actually, the amount of data that I'm working with is so small. I don't really need to use the GPU. I don't need to copy stuff back and forth. Let's just use the CPU. It's perfectly fast enough. Remember how well it worked when I had my own silly little JavaScript library? So let's use the CPU. And I think you'll find that now it's still running like kind of slow. I have a feeling this console log is definitely making things kind of unhappy. So let's take out that console log and let's refresh, and there we go. So now it's performing pretty well. Is it as fast as it was before? I don't know. Could I get back up to 500? But it's better. But But now we have a problem. Copy. So copy is not a function because I didn't write a function to copy a neural network. So what do I mean by copy a neural network? So normally this isn't something you would necessarily do, but it is fundamental to neuroevolution. And by copying it, I need to say, like, this was a good one. Let's make a copy of it to keep it. And I actually want to copy it, not keep a pointer to it, because I also want to mutate it, and I want to mutate it a bunch of times. So I have to figure out what is the way to copy a model in TensorFlow.js. And ultimately, if you want to try the proper way to do this in terms of neuroevolution would not be to just make a copy to go to the next generation, but to take two of them and make a new one that's kind of a mixture. And when I say mixture, I mean mixture of all these weights. But I'm just going to copy it. So what I need to do is I need to go back to this class again, and I need to say copy. So if I say copy, I could just say return new neural network, and I could just put like input nodes, hidden nodes, output nodes, but it wouldn't have the right weights. So let's think about this. Let's do, I'm going to say copy, model copy equals this.create model. So I'm creating a model which is the same, and I need to create model with, it has that stuff. So I can call create model, and it's going to do it with the right input nodes, hidden nodes, output nodes. Okay. So it's not a copy yet, it's another random neural network. But really, the architecture is the same. So in a sense, I've copied the architecture, I've made a new neural network with the same architecture. Now I need to get those weights. So luckily for me, there is in tf.js, there are two functions called like get weights and set weights. So let's take a look at those functions. So for example, if I go to the console here, and I were to say something like, can I say let n equal new neural network, what is it, 852, right? No, 528, 582. So I'm making one of those. And so n.model is that model itself. And you can see it's got all that data in there. So what I want to do is say n.model get weights. No? Oh, I said mode. I want to say n.model, can I just click here? Model get weights. These are all the weight matrices. Why are there 4? Shouldn't there just be 2? Well, there's 4 because there are the weights and the biases. 1, 2. The weights and the biases. 3, 4. So that is what is here. So all I need to do is take these weights and copy them. So let's see. So I could say constant weights equals this.model get weights. And then I could say model copy dot set weights, weights. And then I could say return new neural network with model copy. Now there's a bit of a problem here that I think I'm going to have to do, but this is pretty decent start, right? Make a model of the same architecture, get the weights from the other one, then put those weights in the new model, and then return it. I think there's going to be a big problem here, but this is kind of the idea. So now, if I were to, what I need to do here is, now I'm making a neural network without giving it the input nodes. I need to basically say, if A is an instance of TF sequential, is that right? Let's see. So if I go back to the console, n.model instance of TF sequential, false. No, TF sequential with a capital? True. Okay, so I need to check if it's a TF sequential object. Then this.model equals A. So in other words, I have 2 ways of creating a neural network. If I pass the constructor an existing model, then I just assign it. Otherwise, I create a new one. However, I've really always got to keep track of this is some redundancy here, because the input nodes, hidden nodes, and output nodes are in the model itself. But let's just add another argument here, and then I can say also, this is awkward, and I could refactor this later. So now I'm also going to always require that I also give it the shape, basically. And so here, when I'm making this new neural network with model copy, I'm also going to say this dot, what is it? Input nodes, this dot hidden nodes, this dot output nodes. Okay? So this is me making that new neural network with the model's copy, and I'm also just giving it the shape also so that it sort of retains that information. So now, I should be able to go back, and we've got a copy function. Let me speed this up. Okay, great. Ooh, cannot read property set weights of undefined. That's not good. Where's copy? This got create model. Huh? All right, let's look at. Oh, create model doesn't return the model. Okay. I've got a little bit of an issue here. Okay, I've sort of made a mistake in the way that I've designed this program. What I want to say is this.model equals this.createModel. And I don't actually want to set it here. I'm going to just make in the createModel function, which is where I'm going to make this a variable, const model. And then I'm going to say model.add, and then I'm going to say return model. So this function, this could be living somewhere else or a static function or something, but it's making the model, and it is in the constructor, it is creating it and returning it and placing it in an instance variable, or here it's creating it and returning it and putting in this copy variable. So that should work better. So let's see. Great. So now I don't have a mutate function. No problem. No problem. This is a way to deal with that. Bird.js line 33. Bird.js line 33. Let's just not bother to mutate. No worries. Don't mutate. Let's speed this up. Let it run for a bit. All right, let it run for a bit. We can sort of see, did it get better? Kind of, but there's only one. They're all making the exact same decisions. So without, two things are wrong here. Number one is without mutation, I can't get any variety. But there's something else that I'm pretty sure is wrong. I'm not 100% sure, but I'm pretty sure is wrong, so I want to protect myself against this, is I haven't really made a copy. So I think in the case of my copy function, which is here, this is the weights as tensors, and I am assigning them to the copy, but they're all being assigned the same tensor. So even though there are multiple models, they're all using the same weight table. So if I were to mutate them, they're all going to mutate in exactly the same way. So I need to really make sure I'm copying them, and there is a function in TF.js called clone, which is to make a new tensor that is a copy of an existing one. So I think what I should do is I should say const weight copies is a new array, and then for let I equals 0, I is less than weights index I plus plus, weights.length. So I'm going to iterate over all the weights, and I'm going to say weight copies index I equals weights index I dot clone. So this is kind of the idea of like sort of deep copying, I guess. I'm not sure if I'm 100% accurate about that, but the idea of actually copying them into a new tensor so it's not the previous one. And then I should be able to set the weights to weight copies. So this should be, this should guarantee that I've really got it copied correctly. So let's do that. I'll run it again, speed it up a little bit. So it's still converging kind of into it ultimately being just one of them, the one that happened to do the best. But it's not doing that because I haven't properly copied. It's doing that because there's no mutation. And you can see actually that it seems to be taking a little longer to get there. So I think maybe the copying is better now. Okay, so I do need that mutate function. So what do I need? Where was mutate? So I need a function called mutate, and it's getting an argument 0.1, which is presumably the mutation rate. So the process of mutation in a genetic algorithm is to say, look at the genetic information, which is basically like all of these weights and biases, and one by one examine them, and at some probability, adjust it, make it random, change it, mutate it. So that's what I need to do. So it's more involved than just making a copy of the weights. I need to look at every single weight individually and then mutate it 10% of the time. I'm not sure how I'm going to do this, but let's see. Okay. So if I go into neural network and I made a copy function. Now let's look at mutate. So I want to do the same thing. The first thing that I want to do is I want to get the weights. What do I call this? This.model.getWeights. Then I want to maybe have mutated weights. Is a new, just an array. So I get the current weight tables, and then, or weight tensors, sorry, and then I'm going to go through and make mutated weights. So let me, once again, loop over this array. And I'm going to say tensor equals weights index I, because it's a tensor. And then what I want to do, I want to get the values. So I'm going to use data sync again. I want the shape, because I'm going to need that when I convert it back. I think I can just do this. So I need the tensor, which is the data. I'm going to need to retain the shape, because I need to put it back into a tensor, but I want to mutate them. I don't think I can mutate the tensor without looking at the values. Who knows? So now I'm going to go through, and I'm going to say let I equal 0, j. So j equals 0, j is less than values dot length, j plus plus. So the actual weight, which I'll call w, is values index j. And what I want to do is say values index j equals a new random weight. So I could do something like this, right? Just give it, like, I don't actually even need the current weight. I could just make a random one, right? I'm mutating, but only 10% of the time. So this gets a rate. So I could say if random 1 is less than that rate, then make a new weight. I do think this is a case where there might be some benefit to, rather than picking a totally new weight, and I don't know what initialization was used to make the initial random weights. That's probably somewhere in TensorFlow.js, so there might be some operation I could call here. But I'm just going to tweak it. So this is why I want to grab that weight, and I'm going to say weight plus, and I'm going to use P5's random Gaussian function, which basically gives me a random number that's kind of near to, with a mean of 0 and a standard deviation of 1. So it's just going to adjust that weight a tiny bit. So it's like kind of what you might sort of see with gradient descent, dial up, dial down, but I'm just making a total guess. Just dial it some direction. So it's going to equal that. So once that's done, right, I have my weights. I have my weights. Sorry, I'm confused here. All right. This loop is looking at an individual set of weights. It might be between inputs and hidden, or between hidden and outputs, or it might be one of the biases of either of those weights. And I have it as a tensor. I then have its values. Now I've mutated those values. Aha, I need to make a new tensor. New tensor equals TF tensor, and give it those values again, right? The mutated values with the shape. So this is what's nice. I don't have to worry about what the original shape was. Data sync is just going to flatten everything and give me all the numbers. Pretty sure, I think. And then what I can do is then mutate those, it's flat, and I can put it back into a tensor with the same shape, and it should be back just like it was before. I can say mutated weights. Oh, wait a sec. Yeah, mutated weights index I is now that new tensor. So So I grabbed the tensor, I got its shape, I got the values, I mutated them, I made a new tensor, and it's going to go into my new array of mutated weights. And then when that's done, I can say this.model.setWeights, mutated weights. I think this is mutation. I can't believe, I would be shocked if I didn't make a mistake here. Well, I know one mistake that I made. So there's like a really weird, there's a thing that, and this is something that, thank you to the creators of TensorFlow.js, thank you, sorry. There is one mistake here, which is that data sync is actually not making a copy of the values. So I'm still going to be stuck with a lot of things pointing to the same exact data. So if I mutate one and it's copied for like a bunch, all those are going to get mutated in the same way. And I want to have a bunch of different mutations happening in parallel. So the fix to this, hold on, let me pull up the discussion of this. tf.js, github.com, Schiffman. TensorFlow, oh, hold on. Just give me a second to find. Oh, it's 1:45, but I'm really close to being done. TensorFlow.js examples, issues, closed. I discovered this issue around data sync in this discussion, and thank you so much to one of the creators of TensorFlow.js, Nikhil Thorat, who answered my question about this. So data sync is mutating, I'm mutating the underlying values in the tensor. Apparently there's an array sync function that I could use instead of data sync that does an actual copy, but a coding trained viewer actually suggested that I just call .slice, which is a JavaScript function for copying the array. So this I really, really need in there, because I really got to make sure that I'm not mutating the same underlying information. So I shouldn't add .slice here, and then I think I have this done. We're about to find out. You know, the only way to find out, I mean, there's other ways to find out, I'm sure, is to let this run for a while and to sort of see if it gets anywhere. So I'll let that do that for a little while. So I would say that this worked because there we go. I have an agent that learned basically, again, this is a very simple problem for it to solve, but this technique that I've now done, there's no reason why it couldn't be applied to a more complex scenario. So I now have NeuroEvolution with TensorFlow.js, but I'm not finished. I could do this in the next part, but there's a huge problem here. I haven't thought at all about memory management. And if I do tf.memory in the console, I have 28,870 tensors, and I'm using all these bytes, and if I start from the beginning, I have that many tensors, and look how it's going up. So I'm leaking memory like crazy. I'm not cleaning up any of the tensors that I'm using. And so the way to do that, I don't know why I'm coming over here, but it's very important. In addition to the getWeights and setWeights function, there are two functions that I really need to be conscientious about when working with TensorFlow.js. One is tf.tidy, and this is a function that you can basically give it a callback, and any code that you put up in there, it'll do the cleanup for you. So it's kind of like TensorFlow.js's garbage collection feature. It's like, just put some code in here, and don't worry, we'll take care of disposing memory that's not used. So this is probably what I'm going to use most of the time, but any tensor I could also individually call dispose on when I'm not using it anymore. So let me go and find everywhere in my neural network code that I'm using tensors and make sure I'm cleaning up memory that's not being used anymore. All right, so I'm in my code, scrolling. This should be fine. I don't think I need to dispose models. Maybe I do. But here, okay, oh, look at this mutation. So I'm creating new tensors, I'm doing stuff. This is definitely a place where I want to say tf tidy. And basically, the nice thing is it's literally as simple as this. I just put everything inside of tf tidy. So maybe there's a slightly more optimal, better way of doing this, but this should work. In predict, this one's a little easier. Like I could say like, oh, I don't need the x's anymore. So dispose of those. And now once I have the outputs, I can dispose of the y's. So I could put manual dispose in here. Like that's me disposing, but I think I probably will. Also just use tf tidy. Same exact thing. But there's something else that I need to do here. Because this code is returning something, I need to return the result of tf tidy. So that should be fine. I feel like the model stuff is fine. This should be all the cleanup that I need. Let's see. Copy. Oh yeah. I guess let's do tf tidy in here also. Tf tidy. Let's do this. I also need to say return since I'm returning a new model. I mean, I could put tf tidy in this. Let's see if I need to. Let's look at the memory now. So there's 1,000 tensors. That makes sense because I have 250 birds and there's 4 tensors, 4 weight matrices. That's 1,000. So 3,000. Oh, I missed something. So every generation, I'm keeping some of the old tensors that I don't need anymore. So let's try putting, I suppose, tf tidy here. And also return. And let's see what happens. Oops. Wait, something undefined. What did I mess up? Tf tidy. That's weird. Let's take this out. Okay, so that causes an error, but once I hit the next generation, I've got 1,000 more. Oh! All right. Okay. That didn't seem to work, but I have a better idea. I don't know why that didn't work. There's probably a very good reason, and I will hear from somebody about it. But I think I know what I should do. Where am I copying? Here. Oh, but I have tf tidy here. I was thinking that once I make this new neural network, I would call dispose on the existing model. Where? I don't know where I have my memory leak, to be honest with you. Like, nothing needs to tidy here because, oh, wait a second. No. Dispose the old generation. I mean, ultimately what I'm thinking I need to do is say this dot model dot dispose. Let's just see what happens there. 1,000. It's already disposed, so that makes no sense. what am I missing? And I couldn't put it here. I'm totally lost here. This should really be a function outside of the class. I'm not disposing the old birds. All right, hold on. Those have once a bird hits a pipe, you are hidden. Those have a model with tensors. Oh. All right, hold on. That could be it. Update next generation. Next generation, calculate fitness, birds, saved birds. Big one. Oh. Where's calculate fitness? Oh. So maybe like these. Like this. Let's see here. Oh. Oh, there we go. There we go. That was it. Okay. All right, that's it. Okay, after examining this for a bit with a little bit of help from the chat, it looks like the issue that I have is that, and it's a little bit weird what I'm doing here, I have a bunch of different arrays. I have birds, saved, and saved birds. So saved birds is kind of like the previous generation, and then I make all these new birds for the next generation, put them in the birds array. But the models, the saved bird models still exist. So I need to dispose those. And so the way I could do that is just find the place where I'm done making the next generation and then iterate over the saved birds. And a way I could do that is I could also, like in the bird object right now, I could add a function called dispose. It's a little silly to do this, but why not? Which just says this.brain.dispose. And then in the neural network class, I now have a function called dispose, which I would say this.model.dispose. So this is sort of a manual disposal of all of the memory that particular model is using. And then somewhere in the sketch, when I call next generation, that makes the next generation. And then I go on, that's in my genetic algorithm, which is here. So this is making the next generation, and then clearing the saved birds. So before I clear the saved birds, I think it's, I can just use this total value. what I can do now is I can say saved birds index I.dispose. So that should call the dispose function, which calls the dispose function, which calls the dispose function. So now it's I'm looking at 1,000 tensors, and then let me speed this up so it gets to the next generation faster. Oh wow, it just got like a good one. Next generation, and now still 1,000 tensors. So this is really complete. I mean, there's so much more that I could do, but this is complete in terms of the idea of NeuroEvolution with TensorFlow.js and this particular Flappy Bird game. All right, so what's coming next? What could you do? What could I do next? So one thing is, in my previous coding challenge, I saved the model to reload later, and TensorFlow.js has functions for doing that. Save and load layers model. I forget what the names of the functions are called, but they're in there. So I could come back and add that to this. The other thing would be to apply this idea to different scenarios, to different games, to different environments. One of the things that I would like to do is work with steering agents, whether they're finding food or avoiding predators. That would be an interesting thing to try. So hopefully I'll come back and do this same idea, but with a different environment that maybe has more complexity to it with a less obvious result. Because I have a feeling that I could have gotten a bird to solve this game with just some if statements. Like I could probably guess, like, oh, you should always jump if you're too high. You shouldn't jump if you're higher than where the pipe opening is, and if you're lower, you should jump. So I could write an if statement. Instead, I've used a neural network. Thank you for watching. If you make your own version of this, if you have ideas for how to make this better, please let me know in the comments. And also over at thecodingtrain.com, you can submit a link to your version of this are running in the browser, and I'll take a look at those and hopefully share them in a future video or live stream. Thanks for watching, and goodbye. All right. Black hole, NeuroEvolution, stack. I did everything I said I was going to do. I recorded to disk. I'm done for the week. There will be no live stream next Wednesday. The next time you will see me is hopefully 2 weeks from today. The way to find out when I'm live streaming is to subscribe. Don't smash the button. Just like click it very gently and nicely. If this were my subscribe button, I would do this. Hello. Say subscribe. Thank you. There's an alarm bell. You could click that if you want, but only if you want. You don't want to be. Notifications are so annoying. Reduce those in your life. But that's why I tend to schedule them either the day of or the day before, so you'll see them pop up in your feed. Random numbers. I think to round out this, yeah, Joshua Burke in the chat is saying, try using this as a base for running your own Pong game agents. Exactly. I definitely want to do that. To round out the day, to the tune of my Flappy Bird neuro-evolved agent, 613-831-7222, 552-341-8963, 390-06-93504, 1-823-734-9815, 520-802-69675, 72651. 159732405, 82081022114, 5714-143-353-526-471994, 9452673-253, 32215-30094, 872-7656-896, 15625325594. Don't you feel relaxed? Deep breathing, policy gradients, minimax, reinforcement learning, frozen lake, Q learning. There's too much in this world. I can't do it all, people. I'm trying my best. I have to admit, I'm a little bit overscheduled this month, and I think it's good for me not to be here next week to sort of rebuild some strength and catch up on some things, but also I'll be out of town. So thank you for everyone who supports me, whether you're just watching, signed up to Patreon, clicking on the brilliant.org sponsor link. All those things are super helpful. It kind of motivate me, helps me kind of build the resources to do this stuff more. And I appreciate it very much. So I will see you all 2 weeks from today. Stay tuned for edited versions of these videos coming out, although maybe you don't want to watch those because you're watching right now. And thank you very much.
As always, I always forget the this dot, this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do dot, this dot, this dot, this dot, this dot song. This dot, this dot. This
Bye, everybody.
Never forget this dot, this dot, this dot, this dot, this dot song. This dot, this dot, this dot. Never forget this dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot, this dot song. This dot, this dot, this dot. Never forget this dot. This dot, this dot, this dot. Never forget this dot. I'm gonna do the this dot, this dot, this dot, this dot, the this dot song. Never forget the this dot. Somebody compose that song for me.